Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of Earth's most catastrophic volcanic eruption and the world it remade in fire and ice. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the highlands of northern Sumatra, Lake Toba stretches like a mirror beneath tropical skies. The water moves gently against volcanic shores, lapping at beaches of pumice and obsidian that remember a different world. Morning mist rises from the surface in gauzy columns, dissipating into air that carries the scent of frangipani and wood smoke from lakeside villages. The sound of water against stone creates a rhythm so gentle it might be mistaken for breathing, the slow, steady respiration of a landscape at rest. Tourists paddle kayaks across the surface, their wake spreading in perfect V-shapes behind them, unaware that beneath their feet lies one of Earth's most violent secrets. Children from the villages swim in the shallows, their laughter echoing across water that holds memories of fire. Fishermen cast nets from traditional boats carved from single trees, painted in brilliant blues and reds that mirror the tropical sky. Their catches swim through water columns that extend down into darkness, where volcanic debris has accumulated for millennia. The lake extends 100 kilometers from north to south, 30 kilometers from east to west. A body of water so vast it generates its own weather patterns. Clouds form above its center on clear afternoons as heated air rises from the dark surface, creating thermals that eagles ride in lazy spirals. Local fishermen know the lake's moods intimately, how it can shift from glassy calm to white-capped fury within an hour, how certain winds bring rain while others carry only the promise of storms that never come. They read the water's surface like ancient mariners reading the sea, understanding that this lake follows patterns older than human memory. The lake's depth varies dramatically from shoreline to center. Near the edges, water barely covers beds of volcanic sand where children can wade and search for smooth fragments of obsidian. But toward the center, the lake floor plunges to depths exceeding 400 meters, deep enough to submerge the Empire State Building with room to spare. Sonar measurements reveal a complex underwater topography of ridges and valleys, the collapsed remnants of what was once a mountain range before the Great Eruption reshaped everything. This placid expanse rests within a caldera, a collapsed volcanic crater that formed in a single moment of planetary fury 74,000 years ago. The Toba Supervolcano expelled 2,800 cubic kilometers of material into the atmosphere, enough ash and rock to bury the entire state of Rhode Island under a layer 3 kilometers thick, enough to fill Lake Superior twice over. The eruption ranks as a magnitude 8 on the Volcanic Explosivity Index, the largest volcanic event in the past 2 million years of Earth's history. Only a handful of such eruptions have occurred in the geological record, each one capable of altering global climate for decades. Each one a reminder of the immense forces that operate beneath Earth's deceptively stable surface. The volume of material expelled defies easy comprehension. If loaded onto freight trains, the volcanic debris would form a continuous line of cars stretching from Earth to the Moon and back again. The energy released exceeded that of every nuclear weapon ever detonated by a factor of several thousand. Yet this incomprehensible violence occurred in what geologists consider an instant. The entire eruption likely unfolded over a period of just days or weeks. The caldera walls rise gently from the water's edge, their slopes softened by millennia of tropical rainfall. Bamboo forests cascade down the mountainsides in endless green waves, punctuated by clearings where coffee plants grow in the volcanic soil that remains extraordinarily fertile even after all these millennia. The ash that once darkened skies across continents now nurtures some of the most productive agricultural land in Southeast Asia. Rice terraces climb the hillsides in geometric patterns, each terrace a testament to human adaptation to this volcanic landscape. Small villages dot the shoreline like scattered pearls. Parapat with its bustling market and ferry terminal. Ballage, where traditional weaving patterns incorporate motifs that echo the lake's oval shape. Pangururan on Samosir Island, where people live entirely within the caldera itself. The residents fish in waters that once boiled with molten rock. Their nets pulling up tilapia and carp that swim above layers of volcanic debris hundreds of meters thick. The fish themselves carry trace elements in their bones that geochemists can analyze to understand the lake's deep water chemistry. Only the shape of the land betrays its violent origin. Satellite images reveal the perfect oval outline visible from space, a geometric precision that speaks of catastrophic collapse rather than gentle erosion. The caldera's rim forms an almost complete circle, broken only where the Asahan River has carved an outlet to the sea over thousands of years of patient flow. This single river carries the lake's overflow to the Indian Ocean, bearing with it microscopic particles of ancient volcanic glass that will eventually settle on ocean floors thousands of kilometers away. Hot springs still bubble along the lake's margins, their sulfurous waters reaching temperatures that would scald unwary bathers. Local people have learned to use these natural heat sources for cooking and bathing, building small pools where the mineral-rich water is allowed to cool to comfortable levels. The springs carry dissolved minerals from deep within Earth's crust, painting the rocks around them in vibrant yellows and oranges where sulfur compounds precipitate from solution. Scientific instruments detect magnetic anomalies in the bedrock below, signatures of the massive intrusions of magma that once fed the ancient eruption. These magnetic patterns tell stories of molten rock that cooled and solidified in enormous chambers far beneath the surface. Gravity measurements reveal density variations that map the hidden architecture of the volcanic system. Chambers and conduits through which magma once flowed like underground rivers of fire. Scientists studying the lake's sediments find layers of volcanic debris extending far beneath the current lake bed. Each core sample extracted from the depths tells the same story: periods of quiet accumulation interrupted by catastrophic deposition events. The drilling process itself requires remarkable precision, as the cores must be preserved exactly as they existed in the lake bottom, each layer maintaining its original position and composition. The deepest layers contain fragments of a world that existed before the Great Eruption, pollen from vanished forests, microscopic organisms from ancient lakes, the compressed remains of ecosystems that disappeared in a single day. These fossils speak of a landscape utterly different from today's verdant highlands, a world of different trees, different creatures, different patterns of wind and rain. The pollen grains, preserved by the lake's anaerobic bottom waters, reveal forests of species that no longer exist in this region, suggesting that the eruption fundamentally altered not just the immediate landscape, but the entire regional climate. Some plant species appear to have vanished entirely from the fossil record after the Toba event, possible casualties of the volcanic winter that followed. The sediment cores reveal their secrets reluctantly. Geologists must analyze each layer grain by grain, identifying volcanic ash particles that traveled thousands of kilometers, distinguishing debris from the Great Eruption from material deposited by smaller, more recent events, under microscopes. Individual ash particles display the characteristic shapes and chemical signatures that allow scientists to trace them back to their source. The work requires extraordinary patience, the kind of slow, methodical observation that matches the geological timescales they study. Each sample represents years of accumulated material compressed into centimeters of rock. How strange that such devastation now cradles one of Indonesia's most peaceful landscapes. The Batak people have lived along these shores for centuries, developing creation myths that speak of cosmic battles and world-ending floods. oral traditions that may preserve some distant memory of the catastrophe that shaped their homeland. They call the lake Danau Toba, never knowing that their ancestors might have witnessed its birth from the ashes of the Old World. Their traditional architecture incorporates symbols and patterns that some anthropologists suggest might represent ancient memories of volcanic activity, stylized representations of eruption columns and ash clouds woven into textiles and carved into ceremonial objects. The lake's greatest mystery lies not in its violent past but in its deceptive present tranquility. Beneath the sediments and water, the magma chamber that fueled the ancient eruption has never truly gone dormant. Ground deformation studies reveal that the caldera floor continues to rise and fall in cycles lasting decades, breathing like some vast geological lung. GPS stations positioned around the lake's perimeter measure movements of mere centimeters, but these tiny shifts represent the slow circulation of molten rock far below. Modern seismographs detect small earthquakes occurring regularly beneath the lake, most too faint to be felt by residents but significant enough to indicate ongoing geological activity. The earthquake patterns suggest that magma continues to move through deep conduits, following pathways established during the original eruption. This persistent activity reminds scientists that supervolcanoes operate on timescales that make human civilization appear as brief as a single breath. The supervolcano sleeps, but it dreams still of fire. In laboratories around the world, scientists monitor the chemical signatures in Toba's hot springs, searching for changes in gas composition or mineral content that might herald future activity. They analyze the isotopic ratios of helium and carbon dioxide, looking for evidence of fresh magma rising from the mantle. They know that supervolcanoes operate on timescales that dwarf human civilization, that the intervals between major eruptions can span hundreds of thousands of years. Yet they watch and wait, knowing that beneath the serene surface lies a power that once changed the face of the world and could do so again. Beneath Lake Toba's placid waters, the story begins not with violence but with the slow patience of geological time. Deep within Earth's crust, 20 to 30 kilometers below the surface, heat accumulates in chambers that have been forming for over 1 million years. The process unfolds with the deliberate rhythm of planetary breathing. Magma rising from the mantle, cooling, crystallizing, then melting again as fresh heat arrives from below. This is a story told in temperatures that would vaporize human bone, in pressures that could compress diamond, in timescales that render civilizations as brief as mayfly dances. The Indo-Australian plate slides beneath the Eurasian plate in a process geologists call subduction, one of Earth's most fundamental mechanisms for recycling crustal material. The movement occurs at the stately pace of fingernail growth, mere centimeters per year, note. Yet over millions of years, this glacial motion has consumed entire ocean basins. Ocean floor that once lay beneath ancient seas, bearing the accumulated sediments of countless marine organisms, now descends into the mantle like some vast, slow-moving conveyor belt carrying the detritus of former worlds into Earth's recycling furnace. The descending oceanic crust carries with it a comprehensive record of its journey across the sea floor. Layers of deep-sea sediments contain fossilized remains of microscopic organisms that once floated in ancient oceans. Radiolarians with their intricate silica skeletons. Foraminifera with their calcium carbonate shells. Basaltic rocks formed at mid-ocean ridges bear the chemical signatures of mantle material extruded onto the ocean floor. Seawater, having infiltrated the crust through countless fractures during its oceanic voyage, remains trapped within mineral structures like serpentine and chlorite. As this oceanic crust sinks deeper into Earth's interior, increasing pressure and temperature cause profound transformations. At depths exceeding 100 kilometers, the rock encounters temperatures approaching 800 degrees Celsius, hot enough to begin releasing water trapped within its crystal structure through dehydration reactions. This liberated water carries dissolved elements and compounds that will fundamentally alter the composition of the overlying mantle wedge. These ascending fluids trigger a process known as flux melting, allowing rock to melt at temperatures several hundred degrees lower than would be required for dry melting. The newly formed magma, less dense than the surrounding solid rock, begins its own journey upward through fractures and zones of weakness in the crust. The ascent takes place over thousands of years, a journey measured not in human lifetimes but in the rise and fall of ice ages. During its ascent, the magma encounters varying conditions that cause it to evolve through processes of magmatic differentiation. The magma pauses at different levels, accumulating in chambers where it can cool and undergo crystallization. These temporary reservoirs become laboratories of geological chemistry, where different mineral phases crystallize and settle according to their density and chemical affinity. The process resembles an enormous, slow-motion distillation, operating at temperatures that glow cherry red in the darkness of the deep crust. As cooling proceeds, the first minerals to crystallize are those with the highest melting points, olivine and pyroxene, dense iron and magnesium-rich phases that settle toward the bottom of magma chambers. Their removal from the liquid changes the magma's composition, making it progressively more silica-rich and enriched in elements like potassium and sodium. This evolution process, known as fractional crystallization, can transform a basaltic magma derived from the mantle into the rhyolitic composition characteristic of explosive supervolcanic eruptions. At depths where few earthquakes penetrate, vast reservoirs of rhyolitic magma slowly assemble through this differentiation process. The silica-rich composition that results contains approximately 75% silica by weight, compared to only 50% in the original basaltic magma. This compositional evolution proves crucial to the eventual explosive potential, as high silica magmas possess dramatically different physical properties than their basaltic parents. The high silica content increases viscosity by several orders of magnitude, creating a magma with the consistency of thick honey at temperatures where steel would flow like water. This viscosity proves crucial to the eventual explosive potential, as it effectively traps volcanic gases that would otherwise escape gradually to the surface. Water vapor, carbon dioxide, and sulfur compounds accumulate to concentrations that approach saturation limits, dissolved in the magma like gases in a champagne bottle, building pressure over geological time. The capacity of rhyolitic magma to dissolve water reaches approximately 6% by weight under the pressure conditions existing at depths of 10 to 20 kilometers. This represents an enormous volume of dissolved gas, enough water vapor in a cubic kilometer of magma to fill a lake several kilometers across when expanded to atmospheric pressure. The achievement of such high volatile concentrations requires both the appropriate chemical composition and the extended residence times that allow equilibrium dissolution to occur. Scientists studying similar volcanic systems worldwide have identified the precise conditions necessary for supervolcanic eruptions through decades of research at active calderas like Yellowstone, Long Valley, and the Campi Flegrei. The magma chamber must reach a critical size, typically several hundred cubic kilometers of eruptible material, a volume comparable to Lake Erie, filled with molten rock at temperatures exceeding 700 degrees Celsius. The melt fraction within the chamber must exceed a threshold where liquid magma can move freely through what volcanologists term a crystal mush. Most importantly, the chamber must reach a state of gas saturation, where dissolved water vapor begins to form bubbles, dramatically reducing the magma's density and creating the buoyancy necessary for rapid ascent. This critical transition occurs when the magma contains its maximum possible concentration of dissolved water at the prevailing pressure and temperature conditions. The Toba system accumulated these conditions with the inexorable patience of deep time. Seismic studies of similar calderas suggest that the chamber grew through repeated injections of fresh magma from below, each pulse adding volume while also reheating and remobilizing existing material. These injections likely occurred episodically, triggered by deep crustal processes or changes in the regional stress field related to plate tectonic motions. Each magma injection brought not only additional volume, but also fresh heat that prevented the chamber from solidifying completely. Computer models suggest that the system required a delicate balance, sufficient heat input to maintain mobility, but not so much that rapid eruption occurred before critical volumes could accumulate. Temperature gradients within the chamber created complex circulation patterns as hotter magma rose along the chamber walls while cooler material sank toward the center. These convective currents, operating over timescales of tens of thousands of years, mixed and homogenized the magma to create the uniform composition that characterizes large ignimbrate eruptions. The circulation also concentrated volatile compounds through vapor phase transport with gas bubbles rising toward the chamber roof and creating a stratified system with gas-saturated magma at the top and crystal-rich, degassed material at the bottom. Crystallization studies of Toba's volcanic deposits reveal precise details about pre-eruption storage conditions. The presence of specific mineral phases like sanidine feldspar and quartz, combined with the absence of others like olivine or pyroxene, indicates a magma storage temperature of approximately 750 degrees Celsius. This temperature represents a critical threshold, hot enough to maintain mobility but cool enough to allow significant crystal growth and volatile concentration. The chamber's roof, composed of older volcanic rocks and sedimentary formations, gradually thinned as the magma body grew. The expanding chamber created fracture networks that allowed hydrothermal fluids to circulate through the overlying rocks. This circulation system heated the country rock while weakening it through chemical alteration processes that replace strong minerals with weaker clay assemblages. Surface manifestations of this deep heating remained subtle: hot springs discharging mineral-rich water, elevated ground temperatures creating local climatic anomalies, occasional small earthquakes as rock expanded and contracted. These symptoms provided little warning of the catastrophe brewing below, serving more as geological curiosities than harbingers of global devastation. How remarkable that such immense preparation could proceed almost invisibly. The magma chamber reached dimensions comparable to large metropolitan areas, extending perhaps 50 kilometers in length and 10 kilometers in height. Yet this enormous geological feature gave little surface indication of its presence, hidden beneath kilometers of solid rock like some vast, molten secret. The final approach to eruption likely unfolded over centuries as the chamber approached critical conditions. Gas saturation increased as volatile components concentrated through ongoing crystallization. The chamber's roof underwent progressive weakening as hydrothermal fluids exploited fractures. Small-scale eruptions may have occurred, venting pressure but ultimately contributing to eventual catastrophic failure by creating pathways for larger-scale magma ascent. Contemporary volcanic monitoring reveals that large magmatic systems can exist for hundreds of thousands of years before producing major eruptions. The Yellowstone caldera system has generated 3 supervolcanic eruptions over the past 2 million years, with intervals spanning hundreds of millennia. These timescales dwarf human history, operating according to rhythms that predate our species by orders of magnitude. The mystery that haunts volcanologists involves predicting the transition from slow accumulation to rapid eruption. Modern examples like the Campi Flegrei caldera show that magma chambers can remain active for millennia without producing catastrophic events. The precise trigger mechanisms that initiate supervolcanic eruptions remain among geology's most challenging puzzles. Yet beneath Toba, the trigger eventually arrived, whether through a final injection of fresh magma, critical gas pressure increase, or inexorable roof weakening. The system reached its tipping point. After perhaps a million years of patient preparation, involving processes that began before the first human ancestors walked upright, the supervolcano prepared to remake the world in fire and ash. The chamber that had grown in darkness and silence would soon announce its presence to every corner of the globe. 74,000 years ago, on a morning that began like countless others before it, The accumulated pressure beneath Sumatra reaches a threshold that has been building for millennia. The moment arrives not with fanfare, but with the quiet inevitability of geological law. Gas saturation in the upper reaches of the magma chamber finally exceeds the critical point where dissolved water vapor begins to nucleate into bubbles. The transition occurs as simply as water beginning to boil, yet the consequences will reshape the planet. Deep within the chamber, microscopic bubbles form along crystal faces and within the magma itself, each one a tiny sphere of superheated steam expanding against the immense pressure of overlying rock. The process follows physical principles understood by modern scientists, but operating at scales that dwarf laboratory experiments. As bubbles grow and coalesce, they reduce the density of the magma dramatically, creating buoyancy forces that overcome the weight of kilometers of solid rock above. The initial ascent begins slowly, almost imperceptibly, as gas-rich magma rises through the chamber's upper reaches. Sensitive seismographs, had they existed, might have detected the first subtle tremors as rock adjusted to the movement of molten material. The magma follows pathways of least resistance, exploiting fractures weakened by millions of years of hydrothermal circulation. Each small earthquake represents another barrier overcome, another step toward the surface. Within hours, the rising magma encounters the zone of brittle fracture where rock can no longer deform plastically, but instead breaks catastrophically. The transition from slow ascent to explosive eruption occurs with terrifying speed as the magma accelerates through increasingly fractured rock. Decompression causes dissolved gases to expand exponentially, fragmenting the magma into countless droplets and creating the conditions for one of Earth's most violent natural phenomena. The final moments before surface breakthrough unfold according to fluid dynamics operating at pressures exceeding those found in the deepest ocean trenches. The magma gas mixture accelerates through vertical conduits like a geological rocket engine. Reaching velocities that exceed the speed of sound, the ascending column carves its own pathway through the overlying rock, widening existing fractures and creating new ones through the sheer force of its passage. Surface breakthrough occurs simultaneously across multiple vents as the rising magma finds every available pathway to the atmosphere. The overlying rock, weakened by millennia of heating and alteration, fails catastrophically across an area spanning tens of kilometers. What was once solid ground becomes a series of volcanic vents, expelling material at velocities that defy human comprehension. The eruption begins not as a single explosion, but as a coordinated assault on the sky itself. The eruption column that emerges represents one of the most powerful fluid dynamic phenomena in Earth's history. Magma and gas accelerate from rest to supersonic velocities in mere seconds, propelled by pressure differentials that exceed those driving the most powerful rockets. The mixture of molten rock fragments, volcanic gases, and entrained air rises through the atmosphere like a tower of fire and fury. Climbing toward altitudes where commercial aircraft would one day fly, initial velocities at the vent exceed 300 meters per second, faster than the most powerful hurricanes, faster than the terminal velocity of falling objects. The eruption column operates as a natural jet engine, with expanding gases providing thrust while the surrounding atmosphere provides resistance. The balance between these forces determines the column's ultimate height and the global distribution of volcanic material that will follow. As the column rises through increasingly thin atmosphere, it entrains surrounding air through turbulent mixing processes that multiply its volume exponentially. Cold atmospheric air mixes with superheated volcanic gases, creating convective instabilities that drive the column ever higher. The process resembles the formation of a thunderstorm, but powered by energies that dwarf the most severe weather phenomena. Calculations based on the volume of erupted material suggest that the Toba eruption column reached heights exceeding 80 kilometers, well into the mesosphere, higher than the aurora borealis. In atmospheric regions where the sky begins its transition to the black of space. At such altitudes, the The volcanic material encounters wind patterns and atmospheric dynamics entirely different from those operating at Earth's surface. The column rises through the troposphere, through the stratosphere, and into atmospheric layers where very few natural phenomena penetrate. The eruption's acoustic signature propagates around the globe as infrasonic waves that travel through both atmosphere and solid Earth. These sound waves, too low in frequency for human hearing, carry enough energy to be detected by sensitive instruments thousands of kilometers away. The eruption announces itself to the planet through vibrations that circumnavigate the globe multiple times, each passage slightly weaker than the last but still carrying the unmistakable signature of catastrophic volcanic activity. How strange that such violence should follow laws as predictable as those governing falling stones or flowing water. The eruption operates according to principles of fluid mechanics and thermodynamics that modern engineers use to design rocket engines and industrial processes. Yet the scale transforms familiar physics into planetary catastrophe, demonstrating how the same natural laws that govern everyday phenomena can produce events that reshape continents. The sustained nature of the eruption sets it apart from smaller volcanic events that exhaust their driving pressure within hours or days. The Toba system has accumulated enough gas-rich magma to maintain explosive discharge for days or weeks, continuously feeding material into the eruption column at rates that exceed the flow of major rivers. The chamber empties itself with mechanical efficiency, drawing upon reserves accumulated over geological time to fuel a spectacle that will be remembered in ice cores and sediment layers for millions of years. Eyewitness accounts, had any humans survived in the immediate vicinity, would have described a scene that defies rational comprehension. The horizon transforms into a wall of ascending fire and debris, while the ground shakes with continuous earthquake tremors as the magma chamber empties and the overlying landscape begins its collapse into the void below. The normal rhythms of day and night disappear as the eruption column blocks sunlight across vast areas. The eruption's power output exceeds that of every nuclear weapon ever detonated by factors of thousands. Yet the energy release occurs not as a single pulse, but as a sustained discharge that continues hour after hour. The comparison to human technology breaks down entirely when confronted with geological forces operating at planetary scales. The eruption represents the release of thermal energy accumulated over millions of years, concentrated into a geological instant that will define Earth's climate for decades to come. Within the eruption column itself, temperatures exceed 1,000 degrees Celsius while velocities reach several hundred meters per second. Volcanic bombs, fragments of molten rock ranging from pebbles to house-sized boulders, follow ballistic trajectories that carry them dozens of kilometers from their source. The largest fragments create impact craters when they strike the ground, while smaller particles remain suspended in the atmospheric column for hours or days. The mystery that continues to puzzle volcanologists involves the precise mechanism that triggers such catastrophic eruptions after long periods of quiescence. The transition from stable magma chamber to explosive eruption occurs over timescales too short for human observation. Yet the consequences persist for geological ages. Modern monitoring systems can detect the precursors to smaller eruptions, but supervolcanic events may operate according to trigger mechanisms that remain beyond current understanding. Yet on this morning 74,000 years ago, the trigger operates with deadly efficiency, whether through final gas saturation, roof collapse, or some combination of factors that may never be fully understood. The Toba system crosses the threshold from accumulation to eruption. The chamber that required 1 million years to fill begins emptying itself in a matter of days, launching enough material into the atmosphere to alter global climate patterns and challenge the survival of every living thing on Earth. The eruption column pierces the sky with a violence that transforms the very concept of up and down. 80 kilometers above the Sumatran landscape, volcanic material penetrates atmospheric layers where meteors burn and satellites orbit, carrying Earth's substance into realms normally reserved for cosmic phenomena. The column rises through the troposphere in minutes, punching through the tropopause as if it were tissue paper, ascending through the stratosphere where commercial aircraft will one day cruise, and finally reaching the mesosphere where the aurora dances on clear nights. At such unprecedented heights, the volcanic material encounters atmospheric conditions that exist nowhere else in the human experience. Temperatures drop to minus 90 degrees Celsius, colder than the polar ice caps, colder than the surface of Mars. Air pressure falls to less than 1% of sea level values, creating an environment more similar to the edge of space than to Earth's surface. Yet the eruption column continues to rise, propelled by energies accumulated over geological time and released in geological instants. The physics governing the column's ascent operate according to principles that challenge human intuition. The mixture of volcanic gases and rock fragments behaves as a single fluid and dies, with hot gases expanding and cooling as they rise through decreasing atmospheric pressure. The process follows thermodynamic laws similar to those operating in internal combustion engines, but scaled to planetary proportions and operating in atmospheric conditions that exist nowhere else on Earth. As the column reaches its maximum height, it begins to spread laterally, forming what volcanologists call an umbrella cloud. The ascending material, having reached neutral buoyancy in the thin mesospheric air, can rise no further and instead spreads outward in all directions like water hitting a ceiling. This lateral expansion creates a volcanic cloud hundreds of kilometers in diameter, a man-made addition to Earth's atmosphere that will persist for months and affect global weather patterns for years. Wind patterns at stratospheric and mesospheric levels carry the volcanic material along atmospheric rivers that flow according to pressure gradients and thermal dynamics, operating far above the surface weather systems familiar to ground-based observers. These high-altitude winds operate according to different principles than surface winds, driven by solar heating patterns and the planet's rotation, rather than by local temperature and pressure variations. The westerly winds that dominate the stratosphere at tropical latitudes begin their work of global distribution almost immediately. Material ejected into these high-altitude wind streams travels eastward at velocities exceeding 100 kilometers per hour, completing circuits of the globe in a matter of weeks. The process resembles a planetary-scale conveyor belt, transporting Sumatran volcanic material to every corner of Earth's atmosphere. Volcanic particles suspended at these altitudes experience atmospheric conditions radically different from those at Earth's surface. In the stratosphere, where water vapor concentrations drop to nearly zero and ozone absorbs ultraviolet radiation from the sun, volcanic particles can remain suspended for months or years. The absence of precipitation at these heights means that material ejected into the stratosphere cannot be washed out by rain or snow, ensuring global distribution before eventual gravitational settling. The size distribution of particles within the volcanic cloud follows power laws that govern fragmentation processes throughout nature. The largest fragments fall out quickly under gravitational influence, creating ashfall deposits within hundreds of kilometers of the eruption site. Medium-sized particles remain suspended for days or weeks, traveling thousands of kilometers before settling to Earth's surface. The finest particles, microscopic fragments of volcanic glass smaller than bacteria, remain suspended for months, circulating through global atmospheric patterns multiple times before eventually settling. These microscopic particles carry within their crystal structure the chemical signature of the Toba magma chamber, preserving a record of the eruption that scientists will later identify in ice cores from Greenland and Antarctica, in deep-sea sediments from the Indian Ocean, and in lake deposits from locations as distant as India and China. Each particle represents a fragment of Sumatra distributed globally, a geological calling card left in Earth's archives. The optical properties of volcanic particles suspended in the high atmosphere begin to affect solar radiation almost immediately. Fine volcanic dust scatters incoming sunlight more efficiently than clear air, reducing the amount of solar energy reaching Earth's surface while simultaneously absorbing and re-radiating energy at infrared wavelengths. The net effect creates a planetary sunshade that will persist for years, gradually diminishing as particles settle under gravitational influence. Calculations based on the estimated volume of fine particles suggest that the Toba eruption reduced global solar radiation by several percent, enough to trigger measurable cooling of Earth's surface temperature. The reduction operates through well-understood physical principles involving the scattering of electromagnetic radiation by suspended particles. The same physics that makes sunsets red and skies blue, but scaled to global proportions and persisting for timescales measured in years rather than minutes. The chemical composition of Toba's volcanic gases adds another dimension to the eruption's atmospheric impact: sulfur dioxide, released in quantities measured in millions of tons, reacts with water vapor in the stratosphere to form sulfuric acid aerosols. These microscopic droplets prove even more effective than solid particles at reflecting solar radiation, creating a secondary cooling effect that amplifies the initial impact of volcanic dust. The formation of sulfuric acid aerosols follows chemical pathways that operate slowly by human standards but rapidly by geological measures. Sulfur dioxide molecules react with hydroxyl radicals and water vapor through a series of intermediate steps, ultimately forming droplets of concentrated sulfuric acid suspended in the stratosphere. The process requires weeks to months to reach completion, but the resulting aerosols remain suspended for years, extending the eruption's climatic impact far beyond the initial explosive phase. How remarkable that chemistry operating at molecular scales should influence global climate patterns affecting entire continents. The same sulfur that once lay dissolved in Toba's magma chamber now participates in atmospheric reactions that will alter precipitation patterns across Asia, affect growing seasons in temperate regions, and contribute to the advance of glacial ice in polar areas. The eruption transforms local geological material into global atmospheric phenomena, demonstrating the interconnected nature of Earth's various systems. The stratospheric circulation patterns that distribute Toba's volcanic products operate according to dynamics driven by solar heating and planetary rotation. The Brewer-Dobson circulation, named for scientists who will study it decades later, carries material from tropical latitudes toward the poles through meridional transport cells that operate over timescales of months to years. This circulation ensures that Toba's impact extends far beyond the tropical regions where the eruption occurs. Temperature measurements that will one day be recorded in ice cores from both Greenland and Antarctica will show the global reach of Toba's climatic impact. The volcanic signature appears in polar ice with timing that reflects atmospheric transport processes, earlier in Greenland due to more direct atmospheric pathways, later in Antarctica due to the additional time required for meridional transport across the equator. The ice preserves not just the chemical signature of the eruption, but also a record of its global atmospheric dispersal. The eruption column that began as a localized phenomenon in Sumatra transforms within hours into a global atmospheric perturbation that will influence weather patterns on every continent. Local volcanic violence becomes planetary climate, forcing through the operation of atmospheric transport processes that connect even the most distant regions of Earth's surface. The column that pierces the sky above Toba represents not just a spectacular geological phenomenon, but the beginning of a worldwide environmental crisis that will test the limits of life's adaptability. Satellite imagery, had such technology existed, would have revealed the eruption's global signature within days of the initial explosion. The volcanic cloud expands across the tropical atmosphere like a vast stain, clearly visible against the normal background of water vapor and atmospheric dust. Time-lapse photography would show the cloud's evolution from a localized disturbance to a planetary-scale atmospheric feature, demonstrating how geological processes operating at point sources can influence global environmental conditions. The mystery that continues to fascinate atmospheric scientists involves the precise mechanisms by which volcanic material affects global climate systems. While the basic physics of radiation scattering and aerosol formation are well understood, The complex interactions between volcanic perturbations and existing climate patterns remain subjects of active research. Each major volcanic eruption provides new data for understanding these interactions. But supervolcanic events like Toba operate at scales that exceed the range of modern observations. Yet, 80 kilometers above Sumatra, the eruption column reaches its maximum height and begins its transformation from local geological violence to global atmospheric phenomenon. The material that rose from Earth's depths now spreads across Earth's sky, carrying with it the power to alter climate patterns that have remained stable for millennia. The column that pierces the sky becomes a planetary instrument of change, writing its signature across the atmosphere in letters that will remain legible for years to come. Within hours of the eruption's commencement, volcanic ash begins its descent across vast expanses of the Asian continent, the finest particles that, having reached the stratosphere, will circle the globe for months. But the coarser material follows ballistic trajectories that carry it eastward on the prevailing winds. The ashfall begins as a gentle dusting in regions hundreds of kilometers from Sumatra. But as the eruption continues hour after hour, the accumulation grows from millimeters to centimeters to depths that will bury entire landscapes. The ash that falls consists of microscopic fragments of volcanic glass, each particle a tiny shard of the magma that once lay molten beneath Sumatra. Under magnification, individual ash grains reveal complex shapes and textures that record the violence of their formation. Curved surfaces where gas bubbles were frozen in expanding magma, sharp edges where brittle material fractured under explosive decompression. Each grain carries within its structure the chemical signature of Toba's unique magma composition, creating a geological fingerprint that will allow future scientists to identify this eruption's products anywhere on Earth. The physical properties of volcanic ash create challenges that extend far beyond simple accumulation. The particles possess sharp, angular surfaces that abrade any material they contact, while their fine size allows them to penetrate into spaces normally protected from wind-borne debris. The ash infiltrates mechanical systems, clogs air passages, and creates a dusty coating that adheres to every surface through electrostatic attraction. Even small accumulations transform familiar landscapes into alien environments where normal activities become difficult or impossible. In regions closest to the eruption site, ashfall occurs at rates measured in centimeters per hour, accumulating faster than rainfall during the most severe thunderstorms. The ash falls silently, without the sound of raindrops or the visual drama of precipitation, creating an eerie atmosphere where familiar sounds become muffled and distant objects disappear behind curtains of falling volcanic debris. The normal boundary between earth and sky becomes blurred as ash-laden air reduces visibility to mere meters. The distribution pattern of ashfall follows the complex three-dimensional structure of atmospheric wind systems at different altitudes. Surface winds carry the coarsest particles along relatively simple trajectories, while particles injected into higher atmospheric layers follow more complex pathways determined by wind speeds and directions that vary with altitude. The result creates a complex pattern of ash thickness that reflects the detailed structure of atmospheric circulation during the eruption period. Geological evidence preserved in sediment cores and outcrop exposures reveals the extraordinary extent of Toba's ashfall distribution. Layers of volcanic ash have been identified in locations spanning from Pakistan to the South China Sea, from central India to the islands of Indonesia. The ashfall covers an area exceeding 10 million square kilometers, larger than the entire continent of Europe, with measurable accumulations extending across 20 degrees of latitude and 30 degrees of longitude. In peninsular India, over 3,000 kilometers from the eruption site, ash deposits reach thicknesses of several meters in some locations. These accumulations represent the settling of particles that traveled through the atmosphere for days or weeks, carried by monsoon circulation patterns and upper-level wind systems. The preservation of such thick deposits at such distances testifies to the enormous volume of material ejected by the Toba eruption and the efficiency of atmospheric transport processes. The chemical composition of ashfall deposits varies systematically with distance from the eruption site, reflecting the size-dependent transport processes that govern particle distribution. Proximal deposits contain a higher proportion of coarse particles, with compositions reflecting the bulk magma composition, while distal deposits are enriched in fine particles that underwent more extensive atmospheric transport. These compositional gradients provide detailed information about eruption dynamics and atmospheric transport processes. Analysis of ash layers and deep-sea sediment cores from the Bay of Bengal and Arabian Sea reveals the marine impact of terrestrial ashfall. Volcanic particles that fell into the ocean created distinctive layers in the sedimentary record, interrupting the normal accumulation of marine-derived sediments with pulses of land-derived volcanic material. These marine ash layers preserve not only the chemical signature of the Toba eruption, but also information about ocean circulation patterns and marine ecosystem responses to volcanic perturbation. The interaction between falling ash and existing vegetation creates cascading effects that extend far beyond simple burial. Ash accumulation on leaf surfaces blocks photosynthesis, while adding weight that can break branches or topple entire trees. The fine particles penetrate into plant tissues, causing abrasion damage to leaves and stems. Even relatively thin ash deposits can prove lethal to plants adapted to specific light and moisture conditions, particularly in ecosystems where species have evolved narrow tolerance ranges. Forest ecosystems prove particularly vulnerable to ash accumulation, as trees cannot quickly shed the ash that accumulates on their canopies. The additional weight of ash loading can cause structural failure of branches and entire trees, creating extensive areas of wind-thrown timber that alter habitat structure for decades. The loss of forest canopy allows ash to penetrate to ground level more easily, affecting understory vegetation and soil organisms that normally remain protected beneath the tree cover. Agricultural systems, had they existed in their modern form, would have faced immediate and severe disruption from ashfall accumulation. Crops in the field would have been buried or damaged by the weight and abrasive action of falling particles. Soils would have been sealed by ash layers that alter drainage patterns and create barriers to seed germination. The fine particle size of volcanic ash allows it to form impermeable layers when wetted, transforming agricultural soils into concrete-like surfaces unsuitable for plant growth. Rivers and streams across the ashfall zone begin to carry enormous sediment loads as surface runoff mobilizes the freshly deposited volcanic material. Stream channels that normally run clear become choked with ash-laden water that resembles liquid concrete. The increased sediment load alters channel morphology, causes widespread flooding as streams lose their capacity to carry water, and delivers massive quantities of volcanic debris to downstream environments, including lakes and coastal areas. How extraordinary that particles originating from a single point source should simultaneously affect millions of square kilometers of Earth's surface. The ashfall represents a form of geological precipitation that delivers more material to some regions than they would normally receive through natural sedimentation processes over thousands of years. Landscapes that required millions of years to develop their characteristic forms can be fundamentally altered in a matter of days by the accumulation of foreign volcanic material. The preservation potential of ash layers in the geological record proves remarkably high due to their distinctive composition and rapid emplacement. Unlike normal sedimentary processes that operate gradually over extended periods, ashfall creates discrete, time-synchronous marker horizons that can be traced across vast areas. These ash layers serve as geological time markers, allowing scientists to correlate sedimentary sequences separated by thousands of kilometers and to establish precise chronologies for environmental changes. The optical properties of ash-laden atmosphere create spectacular but ominous visual effects across the regions experiencing ashfall. Sunlight scattered by suspended particles produces enhanced sunset colors while reducing overall light intensity during daytime hours. The sun, when visible through the ash-laden atmosphere, appears as a dim red disk reminiscent of solar eclipses. These atmospheric optical effects provide visual confirmation of the eruption's global reach to observers thousands of kilometers from the source. Modern atmospheric modeling suggests that the ash fall from the Toba eruption continued for weeks or months as the eruption column maintained its massive output and atmospheric circulation patterns distributed the material across ever wider areas. The sustained nature of the eruption ensured that regions initially spared by wind direction changes eventually received significant ash accumulations as circulation patterns shifted and the volcanic cloud expanded. The mystery that challenges modern volcanologists involves understanding how ecosystems respond to such massive and rapid environmental perturbations. While smaller volcanic eruptions provide some analogies, the scale of the Toba ashfall exceeds any event in recorded human history. The biological and ecological consequences of burying vast areas under meters of volcanic debris remain subjects of active research and debate among scientists studying mass extinction events. Yet across Asia, the ash continues to fall with mechanical persistence, covering forests and grasslands, filling valleys and coating mountainsides, transforming familiar landscapes into uniform gray expanses that stretch beyond the horizon. The ashfall represents more than simple burial. It constitutes a fundamental restructuring of surface environments across a significant fraction of Earth's land area. The particles that began their journey in Sumatra's magma chamber now blanket half a continent, carrying with them the power to alter the course of evolution itself. The sulfur compounds ejected into the stratosphere begin their transformation into one of nature's most effective climate-altering substances. Millions of tons of sulfur dioxide, released during the explosive phases of the eruption, encounter the unique chemical environment of the upper atmosphere where water vapor concentrations drop to near zero, and intense ultraviolet radiation drives photochemical reactions impossible at Earth's surface. The sulfur dioxide molecules begin a slow oxidation process that will ultimately produce microscopic droplets of concentrated sulfuric acid suspended in the stratosphere for years. The chemical pathway from sulfur dioxide to sulfuric acid aerosols follows well-understood reactions. But the scale of the Toba eruption creates concentrations of reactants far exceeding those encountered during smaller volcanic events. Hydroxyl radicals, produced by the photodissociation of water vapor and ozone, react with sulfur dioxide molecules in a series of intermediate steps that eventually yield sulfuric acid. The process requires weeks to months to reach completion, but the resulting aerosols prove far more effective than solid ash particles at reflecting incoming solar radiation. These microscopic sulfuric acid droplets, typically less than 1 micrometer in diameter, possess optical properties that make them extraordinarily efficient at scattering visible light while remaining relatively transparent to infrared radiation. The asymmetry in their interaction with different wavelengths of electromagnetic radiation creates a powerful cooling effect as more solar energy gets reflected back to space than terrestrial heat gets trapped in the atmosphere. The droplets essentially create a planetary air conditioning system powered by volcanic chemistry. The stratospheric residence time of these aerosols extends their climatic impact far beyond the initial explosive phase of the eruption. Unlike ash particles that settle under gravitational influence within months, sulfuric acid aerosols can remain suspended for 2 to 3 years in the stratosphere. This extended residence time allows the aerosols to circulate through global atmospheric patterns multiple times, ensuring that their cooling effect reaches every region of Earth's surface with relatively uniform intensity. Atmospheric circulation models suggest that the Toba aerosols reduced incoming solar radiation by approximately 6% globally, a reduction sufficient to lower average surface temperatures by several degrees Celsius. The cooling effect operates through straightforward radiative physics, but the magnitude exceeds that produced by any volcanic eruption in recorded history. The temperature reduction approaches the threshold necessary to trigger significant changes in global climate patterns, particularly in regions where ecosystems operate near critical temperature limits. The geographic distribution of cooling effects varies with latitude and season due to differences in solar radiation intensity and atmospheric circulation patterns, tropical regions, receiving the most intense solar radiation, experience the greatest absolute reduction in energy input. However, high-latitude regions, where ecosystems already operate near temperature thresholds for biological activity, prove most sensitive to even modest temperature reductions. The volcanic winter affects different regions through different mechanisms, but with globally significant consequences. Monsoon circulation patterns, which govern precipitation across much of Asia, prove particularly sensitive to changes in temperature gradients between land and ocean surfaces. The volcanic cooling reduces the thermal contrast that drives monsoon systems, weakening the atmospheric circulation patterns that bring seasonal rainfall to billions of people in South and Southeast Asia. The disruption occurs through well-understood atmospheric dynamics, but the consequences extend far beyond simple weather changes to fundamental alterations in ecosystem productivity. The weakening of monsoon systems represents more than a temporary meteorological anomaly. It constitutes a breakdown of the atmospheric machinery that sustains some of Earth's most productive ecosystems. Tropical forests that depend on regular seasonal rainfall begin to experience moisture stress as precipitation patterns become irregular and total rainfall decreases. Grassland ecosystems adapted to distinct wet and dry seasons find their yearly cycles disrupted by the altered timing and intensity of monsoon rains. Agricultural systems across Asia face unprecedented challenges as the atmospheric changes affect both temperature and precipitation patterns simultaneously. Crops adapted to specific seasonal cycles of temperature and moisture encounter conditions outside their tolerance ranges. The cooling temperatures extend to growing seasons in some regions while shortening them in others. But the changes in precipitation patterns prove even more disruptive to plant communities adapted to predictable seasonal rhythms. The volcanic winter's impact on global vegetation creates cascading effects throughout terrestrial food webs. Primary productivity declines as reduced sunlight and altered precipitation patterns limit photosynthesis across vast areas. The decrease in plant growth affects herbivore populations that depend on seasonal abundance of plant materials for survival and reproduction. Carnivore populations face secondary impacts as their prey species decline in numbers and reproductive success. Ocean surface temperatures begin to decline as reduced solar radiation affects the thermal balance of marine surface waters. The cooling occurs gradually due to water's high thermal capacity, but the effect proves particularly pronounced in enclosed ocean basins, like the Mediterranean Sea and Bay of Bengal, where circulation patterns limit heat exchange with larger ocean systems. Marine ecosystems adapted to specific temperature ranges begin to experience stress as their thermal environment shifts beyond normal variability. The interaction between atmospheric and oceanic circulation patterns amplifies the volcanic winter's impact through positive feedback mechanisms. Cooler ocean temperatures alter evaporation rates, reducing atmospheric water vapor and further weakening monsoon circulation. The reduced atmospheric moisture content enhances the efficiency of volcanic aerosols at reflecting solar radiation, intensifying the cooling effect. These feedback loops create a self-reinforcing system that prolongs and amplifies the initial volcanic perturbation. Ice sheet margins in polar regions begin to experience net accumulation as reduced summer melting combines with continued winter snowfall. The shift in ice sheet mass balance occurs gradually, but even small changes in accumulation patterns can trigger significant advances of glacial ice over timescales of decades. The volcanic cooling pushes Earth's climate system toward conditions that favor glacial expansion during an already active ice age period. How remarkable that chemistry operating in the stratosphere should influence the behavior of glacial ice thousands of kilometers away. The sulfuric acid droplets suspended above Earth's surface create atmospheric conditions that affect snow accumulation in Greenland and ice sheet dynamics in Antarctica. The volcanic eruption in tropical Sumatra triggers responses in Earth's polar regions through atmospheric connections that operate across all latitudes. The duration of the volcanic winter depends on the gradual settling of stratospheric aerosols under gravitational influence. Computer models suggest that the most intense cooling persists for 2 to 3 years after the eruption, with measurable effects continuing for up to a decade. The prolonged nature of the impact ensures that multiple growing seasons pass under altered climatic conditions, preventing rapid ecosystem recovery and creating sustained pressure on biological communities. Tree ring records from locations around the world preserve evidence of the volcanic winter's impact on forest growth rates. Trees growing during the years following the Toba eruption show characteristic signatures of temperature and moisture stress, narrow growth rings, altered wood density, and chemical compositions reflecting changed environmental conditions. These biological archives provide detailed records of how terrestrial ecosystems responded to the prolonged atmospheric perturbation. The mystery that continues to challenge climatologists involves understanding the complex interactions between volcanic forcing and existing climate variability. The Toba eruption occurred during a period of natural climate change associated with ice age cycles, making it difficult to separate volcanic effects from ongoing climatic trends. The challenge illustrates the complexity of Earth's climate system and the difficulty of predicting responses to large perturbations. Yet across Earth's surface, the volcanic winter proceeds with mechanical persistence. Temperatures drop degree by degree as sulfuric acid aerosols accumulate in the stratosphere. Monsoon systems weaken as thermal gradients diminish. Ice sheets advance as summer melting decreases. The chemical products of a volcanic eruption in Sumatra reshape global climate patterns with effects that will persist long after the ash has settled and the eruption columns have dissipated into memory. The monsoon systems that govern precipitation across vast expanses of Asia begin their gradual failure as atmospheric temperature gradients weaken under the volcanic shroud. The delicate thermal machinery that drives seasonal rainfall patterns operates through pressure differences created by unequal heating of land and ocean surfaces. When volcanic aerosols reduce solar radiation reaching Earth's surface, the temperature contrasts that power monsoon circulation diminish, and the atmospheric rivers that carry moisture from tropical oceans to continental interiors begin to slow and shift their pathways. The Indian Ocean monsoon, which normally delivers life-sustaining rainfall to the Indian subcontinent and Southeast Asia, weakens as the thermal low-pressure systems over heated land masses fail to develop their normal intensity. The process occurs gradually over several seasons, making the change initially subtle but ultimately catastrophic for ecosystems and organisms adapted to predictable seasonal rhythms. Rivers that have flowed for millions of years begin to diminish as their watersheds receive less precipitation, while lakes that have never known drought begin to recede from their shorelines. Across the Indian subcontinent, 3,000 kilometers from Toba's eruption site, the failure of monsoon rains triggers ecological cascades that ripple through entire biogeographic regions. Tropical forests that depend on seasonal moisture begin to experience water stress during periods when they would normally receive abundant rainfall. The stress manifests first in the forest canopy, where the largest trees show signs of leaf loss and reduced photosynthetic activity, then spreads downward through the forest structure as the water table drops and soil moisture becomes limiting. The timing of monsoon failure proves particularly devastating for plant communities because it disrupts reproductive cycles that have evolved to coincide with the specific seasonal conditions. Many tropical plants time their flowering and fruiting to coincide with the onset of monsoon rains, relying on predictable moisture availability for successful seed germination and seedling establishment. When the rains fail to arrive on schedule or arrive with reduced intensity, entire cohorts of plants fail to reproduce successfully, creating gaps in population structure that persist for decades. Grassland ecosystems across Central Asia face equally severe challenges as precipitation patterns shift beyond the range of natural variability. Grasses adapted to specific seasonal cycles of growth and dormancy find their environmental cues disrupted by altered precipitation timing and intensity. The fine balance between different grass species, maintained through competition for water and nutrients during specific seasonal windows, collapses as the environmental conditions that structured these communities no longer operate with their historical predictability. The hydrological cycle that connects atmospheric moisture to terrestrial water resources undergoes fundamental disruption as evaporation rates change and precipitation patterns shift. Rivers that normally carry monsoon-derived water from mountain watersheds to lowland regions begin to show reduced flow rates as their drainage basins receive less precipitation. The reduced river flow affects not only terrestrial ecosystems that depend on riparian water sources, but also coastal environments where freshwater discharge influences salinity and nutrient patterns. Lake levels across monsoon-affected regions begin to drop as reduced precipitation combines with continued evaporation to create negative water balances. Many lakes that have maintained stable levels for thousands of years begin to recede, exposing shoreline areas that have been underwater for millennia. The newly exposed lake margins reveal sediment layers that preserve records of previous environmental changes, creating natural archives of past climate variability that scientists will eventually use to understand long-term environmental patterns. The decline in lake levels concentrates dissolved salts and nutrients in the remaining water, altering the chemical environment for aquatic organisms. Freshwater species adapted to specific salinity ranges begin to experience stress as their habitat becomes progressively more concentrated. Fish populations that depend on seasonal flooding for reproduction find their spawning grounds altered or eliminated entirely as water levels drop below critical thresholds. Wetland ecosystems, which serve as critical habitat for countless species and act as natural water treatment systems, begin to dry as their water sources diminish. The loss of wetland habitat affects not only resident species but also migratory animals that depend on these areas for feeding and resting during long-distance movements. Waterfowl populations face particular challenges as their traditional stopover sites disappear or become unsuitable for their needs. The failure of monsoon systems triggers human behavioral changes that create additional pressure on already stressed ecosystems. Human populations dependent on seasonal rainfall for agriculture begin to concentrate around remaining water sources, increasing competition for limited resources. The intensified use of riparian areas and remaining wetlands accelerates habitat degradation through overuse and resource extraction. Agricultural systems collapse across vast areas as crops adapted to monsoon rainfall patterns fail to receive adequate moisture for growth and reproduction. Wild plant communities that humans depend on for supplemental food sources also decline under drought stress, reducing the carrying capacity of landscapes that have supported human populations for thousands of years. The combination of agricultural failure and reduced wild food availability creates conditions that challenge human survival across entire biogeographic regions. How profound that atmospheric circulation patterns operating at continental scales should determine the fate of individual organisms separated by thousands of kilometers. The weakening of monsoon systems demonstrates the interconnected nature of Earth's atmospheric and hydrological systems, where changes in one component propagate through the entire system to affect distant regions through atmospheric teleconnections that operate faster than biological adaptation can respond. The spatial pattern of monsoon failure reflects the complex topography and atmospheric dynamics of the Asian continent. Mountain ranges create rain shadows that become more pronounced as overall precipitation decreases. While coastal areas experience different impacts than continental interiors, the heterogeneous pattern of drought impact creates a complex mosaic of environmental stress that affects different species and ecosystems through different mechanisms but with similarly devastating consequences. Soil moisture patterns across monsoon-dependent regions begin to shift, as reduced precipitation combines with continued evapotranspiration to draw down water stored in terrestrial systems. The changes in soil moisture affect not only plant communities but also soil organisms that depend on specific moisture conditions for survival and reproduction. Mycorrhizal fungi that form essential partnerships with plant roots begin to decline as soil conditions become unsuitable for their growth and function. The cascading effects of monsoon failure extend through multiple trophic levels as primary productivity declines and habitat conditions deteriorate. Herbivore populations face reduced food availability and water sources, while carnivore populations experience secondary effects as their prey species decline. The ecological relationships that have structured Asian ecosystems for millions of years begin to unravel under the sustained pressure of altered precipitation patterns. Tree mortality rates increase across monsoon-dependent forests as water stress exceeds the tolerance limits of species adapted to regular seasonal rainfall. The death of large trees creates gaps in forest canopies that alter light regimes and microclimate conditions for understory species. The loss of canopy cover accelerates soil drying and creates positive feedback loops that intensify drought stress throughout forest ecosystems. The mystery that continues to challenge ecologists involves understanding how ecosystems recover from such sustained disruption of fundamental environmental cycles. While individual species may possess some tolerance for environmental variability, the simultaneous alteration of temperature and precipitation and atmospheric chemistry creates conditions that exceed the adaptive capacity of many biological communities. The monsoon failure represents not just a temporary weather anomaly, but a fundamental reorganization of environmental conditions across continental scales. Yet across Asia, the atmospheric machinery that has sustained some of Earth's most productive ecosystems for millions of years continues its gradual breakdown. The thermal gradients that power monsoon circulation remain suppressed under the volcanic shroud. Rivers continue to diminish as watersheds receive less precipitation. Lakes continue to recede as evaporation exceeds precipitation. The failure of monsoon systems proceeds with the same mechanical persistence as the volcanic eruption that initiated the cascade, demonstrating how geological events can trigger atmospheric responses that persist long after the initial perturbation has ended. Across the vast continental expanses where monsoon rains have failed, forests that have stood for millions of years begin their slow surrender to darkness and drought. The tropical and subtropical woodlands of Asia, which once formed continuous canopies stretching from the foothills of the Himalayas to the islands of Southeast Asia, fragment into isolated patches as trees succumb to the combined stress of reduced sunlight, altered precipitation patterns, and increasingly desperate competition for dwindling water resources. The forest dieback proceeds through mechanisms that operate with tragic predictability across multiple species and ecosystems. Large trees, which possess the greatest leaf area and thus face the highest water demands, begin to show signs of stress first as their extensive root systems fail to extract sufficient moisture from increasingly dry soils. The stress manifests initially as leaf wilting and premature leaf drop, followed by branch dieback as trees sacrifice portions of their canopies to reduce water demand and maintain critical life functions. Mycorrhizal networks, the vast fungal communities that connect tree roots and facilitate nutrient exchange across entire forest ecosystems, begin to collapse as soil moisture drops below the levels necessary for fungal growth and function. These underground networks, which can extend for kilometers and connect hundreds of individual trees, represent some of nature's most sophisticated biological infrastructure. Their breakdown eliminates crucial communication and resource-sharing pathways that have enabled forest communities to respond collectively to environmental challenges. The death of canopy trees creates expanding gaps in forest cover that allow volcanic ash and increased solar radiation to penetrate to the forest floor, fundamentally altering microclimate conditions for understory species. Plants adapted to the filtered light and stable humidity of intact forest canopies encountered direct sunlight and rapidly fluctuating moisture conditions that exceed their physiological tolerance ranges. The cascade of mortality spreads from canopy to understory as environmental conditions shift beyond the limits that define forest ecosystems. Epiphytic communities, the diverse assemblages of plants that grow on tree branches and trunks without soil contact, face immediate crisis as their host trees weaken and die. Orchids, bromeliads, ferns, and mosses that depend entirely on atmospheric moisture and nutrients derived from forest canopy processes lose their habitat as trees shed leaves and branches. These aerial gardens, which represent some of the most species-rich communities on Earth, disappear along with their supporting architecture. The acoustic signature of dying forests changes as the complex soundscape created by forest-dwelling animals gives way to an increasingly silent landscape. Bird communities that depend on forest canopy habitat for nesting and feeding begin to decline as their habitat disappears. The elaborate dawn choruses that once announced each day across forest regions diminish in volume and complexity as singing birds become fewer and more widely scattered across fragmented habitat patches. Frugivorous animals, which depend on the seasonal production of forest fruits for survival, face starvation as reduced photosynthesis and water stress cause fruit production to decline dramatically. The disruption of frugivory relationships affects not only the animals that depend on fruit resources, but also the plants that rely on these animals for seed dispersal. The breakdown of seed dispersal networks prevents forest regeneration, even in areas where environmental conditions might otherwise support tree growth. Pollination networks collapse as flowering plants reduce their reproductive investment under stress conditions while pollinating animals lose habitat and food resources. Many tropical plants depend on specific pollinators for reproduction, creating intricate coevolutionary relationships that have developed over millions of years. The simultaneous stress on both plants and pollinators breaks these relationships, preventing successful reproduction even among surviving plant populations. Large mammals that require extensive forest habitat for their territorial needs find their ranges fragmented by expanding areas of dead and dying forest. Elephants, tigers, and other wide-ranging species cannot maintain viable populations in the small forest patches that remain intact. Their local extinctions remove key ecological processes including seed dispersal, predation pressure, and nutrient cycling that help maintain forest ecosystem structure and function. The accumulation of dead plant material creates fire hazard conditions that accelerate forest destruction through mechanisms that operate independently of the original volcanic perturbation. Dry conditions created by drought combine with abundant dead biomass to create tinderbox conditions, where fires can spread rapidly across vast areas. Lightning strikes or even spontaneous combustion of decaying organic matter can trigger fires that consume both dead and living vegetation across entire landscapes. Stream corridors, which normally serve as refugia during drought conditions, begin to fail as their water sources diminish and riparian vegetation dies. The loss of streamside forest cover increases water temperatures and reduces the input of organic matter that supports aquatic food webs. Fish populations that might otherwise serve as refugial sources for recolonization find their habitat degraded beyond the point where viable populations can persist. Soil communities undergo fundamental restructuring as the inputs of organic matter from dying vegetation overwhelm decomposer organisms while simultaneously altering soil chemistry and moisture regimes. The rapid influx of dead plant material creates anaerobic conditions in some areas, while the loss of living root systems reduces soil structure and stability in others. Earthworms, soil insects, and microbial communities that maintain soil fertility begin to decline as their habitat conditions change beyond their tolerance limits. How extraordinary that the chemical composition of Earth's atmosphere should determine the fate of individual trees standing thousands of kilometers from any volcanic activity. The forest dieback demonstrates the global reach of atmospheric perturbations and the vulnerability of complex biological systems to relatively small changes in fundamental environmental parameters. Trees that survived ice ages and continental drift succumb to alterations in atmospheric chemistry that reduce sunlight by mere percentages. The geographic pattern of forest mortality reflects the interaction between volcanic climate forcing and regional environmental conditions. Forests growing in marginal habitats, those already experiencing periodic moisture stress or temperature extremes, prove most vulnerable to additional environmental pressure. Montane forests near their altitudinal limits and forests growing in rain shadow areas begin to show mortality first. While forests in optimal habitat conditions show greater resilience to the altered environmental conditions, the loss of forest cover creates positive feedback loops that accelerate further environmental degradation. Areas previously shaded by forest canopies experience increased surface temperatures and more rapid soil drying. The loss of transpiration from forest vegetation reduces local humidity and can alter regional precipitation patterns. The conversion of forest to open habitat changes surface albedo, potentially affecting local climate conditions and making forest recovery even more difficult. Seed banks buried in forest soils represent the genetic archives that could potentially enable forest recovery when environmental conditions improve. However, many tropical tree species produce seeds that remain viable for only short periods. And the extended duration of environmental stress may exceed seed longevity for numerous species. The loss of genetic diversity through seed bank degradation creates long-term consequences for forest recovery that persist long after environmental conditions return to normal. The mystery that challenges forest ecologists involves understanding the threshold conditions that determine whether forests can recover from such extensive mortality, or whether the dieback represents a permanent transition to alternative ecosystem states. While forests have recovered from natural disturbances throughout geological history, the scale and duration of volcanic climate forcing may exceed the resilience capacity of forest ecosystems that evolved under different environmental conditions. Yet across Asia, the silent forests continue their transformation from vibrant biological communities to landscapes of standing dead timber and slowly decomposing organic matter. Canopy gaps expand as more trees succumb to stress. Understory vegetation withers in the altered light and moisture conditions. Animal communities disperse or decline as their habitat disappears. The forest falls silent not with the sudden violence of fire or storm, but with the gradual quietude of biological systems overwhelmed by environmental conditions beyond their evolutionary experience. In the far northern reaches of Earth, where ice sheets have grown and retreated through countless cycles of glacial advance and retreat, the volcanic winter provides the additional cooling necessary to tip the delicate balance toward glacial expansion. The Fennoscandian ice sheet, covering much of northern Europe, begins to thicken as reduced summer melting combines with continued winter snowfall to create positive mass balance conditions. The process occurs gradually, almost imperceptibly at first, but follows the relentless logic of ice sheet physics where small changes in temperature and precipitation can trigger massive responses over timescales of decades to centuries. The Laurentide ice sheet endowed, which covers much of northern North America, responds similarly to the altered atmospheric conditions created by Toba's eruption. Summer temperatures that normally rise high enough to melt significant portions of the ice sheet surface remain suppressed under the volcanic shroud. While winter snowfall continues at normal or even enhanced rates due to altered atmospheric circulation patterns, the net result creates conditions favoring ice accumulation that have not existed for thousands of years. Ice sheet dynamics operate according to physical principles that amplify small initial changes through positive feedback mechanisms. As ice sheets thicken and expand, their increased surface area reflects more incoming solar radiation, enhancing the cooling effect and promoting further ice accumulation. The growing ice sheets also alter atmospheric circulation patterns by creating cold, high-pressure systems that deflect storm tracks and modify regional climate patterns in ways that favor continued glacial expansion. The advance of ice sheet margins occurs through processes that transform entire landscapes with mechanical efficiency. The ice moves forward at rates measured in meters per year, but its progress proves irresistible to any obstacle in its path. Forests that have stood for thousands of years are bulldozed and buried beneath advancing ice. River valleys are filled with ice that diverts surface water flow into new channels. Coastal areas are depressed under the weight of ice masses that can exceed 2 kilometers in thickness. Permafrost boundaries, which mark the southern limits of permanently frozen ground, begin to migrate southward as air temperatures remain depressed under the influence of volcanic cooling. The southward expansion of permafrost zones affects soil development, vegetation patterns, and hydrological systems across vast areas of northern continents. Plants adapted to unfrozen soils find their root systems encountering permanent ice layers that prevent normal growth and reproduction. The hydrological consequences of ice sheet expansion extend far beyond the immediate areas covered by advancing ice. Water that would normally return to the oceans through river discharge becomes locked in expanding ice masses, gradually reducing global sea level. The process operates slowly by human standards but significantly by geological measures, with sea level dropping by meters over the centuries following the volcanic eruption. Marine ecosystems begin to respond to falling sea levels as coastal areas that have been underwater for thousands of years become exposed to atmospheric conditions. Shallow marine environments, which serve as nursery habitat for many fish species and support highly productive biological communities, shrink in area as sea levels drop. The exposure of continental shelf areas creates new terrestrial habitat, but the transition occurs too rapidly for terrestrial ecosystems to colonize the newly available land area effectively. Ocean circulation patterns undergo modification as the changing distribution of land and sea area alters wind patterns and temperature gradients that drive marine current systems. The Gulf Stream, which carries warm water northward along the eastern coast of North America, weakens as temperature gradients between tropical and polar regions diminish under the influence of volcanic cooling. The reduced heat transport to northern Atlantic regions creates additional cooling that reinforces ice sheet expansion. Thermohaline circulation, the global system of deep ocean currents driven by density differences created by temperature and salinity variations, begins to slow as surface water temperatures become more uniform, and ice sheet melting reduces the salinity of polar waters. The weakening of the circulation system reduces the efficiency of oceanic heat transport, creating additional cooling in high-latitude regions where ice sheets are most sensitive to temperature changes. The formation of sea ice around the margins of expanding ice sheets creates additional positive feedback effects that accelerate the cooling process. Sea ice reflects incoming solar radiation much more efficiently than open ocean water, reducing the amount of solar energy absorbed by polar ocean regions. The enhanced albedo effect of expanding sea ice coverage amplifies the initial volcanic cooling and creates self-reinforcing cycles that maintain low temperatures long after volcanic aerosols have settled from the atmosphere. Atmospheric circulation patterns undergo reorganization as the expanding ice sheets create new centers of high pressure that deflect storm systems and alter precipitation patterns across entire continents. The jet stream, which normally flows in relatively smooth patterns around the globe, develops more pronounced meanders as it encounters the altered pressure patterns created by expanding ice masses. These circulation changes affect weather patterns far from the ice sheets themselves, creating drought conditions in some regions while increasing precipitation in others. Tundra ecosystems, which exist in the transition zones between ice sheets and forested regions, begin to experience changes in species composition as cooling temperatures favor Arctic-adapted species over those adapted to warmer conditions. The tree line, which marks the northern limit of the forest growth, begins to retreat southward as growing season temperatures drop below the thresholds necessary for tree reproduction and survival. The migration of ecological boundaries creates opportunities for some species while eliminating habitat for others. Large mammal populations adapted to ice age conditions begin to expand their ranges as cooling temperatures and expanding tundra create favorable habitat conditions. Woolly mammoths, which have persisted in refugial populations during the warmer interglacial period, find their habitat expanding as grassland and tundra ecosystems replace forests across vast areas. However, the same cooling that favors ice-adapted species creates challenges for temperate-adapted species that lose habitat to advancing ice sheets. How remarkable that sulfuric acid droplets suspended in the stratosphere above tropical Sumatra should influence the behavior of ice masses in Greenland and Antarctica. The ice sheet responses to volcanic cooling demonstrate the global connectivity of Earth's climate system and the sensitivity of large ice masses to relatively small changes in atmospheric temperature. Ice that accumulated over thousands of years begins to thicken and advance due to atmospheric chemistry changes that reduce global temperatures by only a few degrees. The rate of ice sheet advance varies with local topographic and climatic conditions, but the general pattern shows acceleration as feedback mechanisms amplify the initial volcanic cooling. Computer models of ice sheet behavior suggest that the cooling induced by the Toba eruption could trigger ice sheet advances that persist for centuries or millennia, long after the volcanic aerosols have disappeared from the atmosphere. The ice sheets possess their own momentum that allows them to continue growing even after the initial cooling stimulus has been removed. Paleoclimate records preserved in ice cores from Greenland and Antarctica will eventually provide detailed documentation of the ice sheet response to Toba's volcanic winter. These records show not only the temperature changes associated with the eruption, but also the alterations in atmospheric circulation patterns and precipitation regimes that accompanied ice sheet expansion. The ice cores preserve annual layers of atmospheric chemicals that record the progression of environmental changes with remarkable temporal resolution. The mystery that continues to challenge glaciologists involves understanding the precise mechanisms that trigger transitions between glacial and interglacial conditions. While astronomical cycles provide the primary pacing for ice age cycles, volcanic eruptions like Toba may serve as triggers that push Earth's climate system across critical thresholds. The interaction between volcanic forcing and natural climate variability remains an active area of research with implications for understanding both past and future climate changes. Yet in the far north, the ice sheets continue their patient advance across landscapes that have known freedom from ice for thousands of years. Summer after summer, the reduced melting allows additional ice accumulation. Winter after winter, continued snowfall adds mass to the growing ice sheets. The ice advances with geological determination, following physical laws that operate independently of the biological crises unfolding in warmer latitudes, demonstrating how Earth's climate system can undergo reorganization that affects every environment from tropical forests to polar ice caps. The world's oceans, which cover 71% of Earth's surface and contain 97% of its water, begin to absorb the toxic legacy of Toba's atmospheric chemistry. Volcanic gases that once rose in towering eruption columns now descend as acid rain, carrying sulfuric acid, hydrochloric acid, and other corrosive compounds into marine waters that have maintained relatively stable chemistry for millions of years. The process of ocean acidification unfolds gradually but relentlessly as atmospheric acids dissolve into seawater and begin altering the chemical environment that supports marine life. The chemistry of seawater reflects a delicate balance of dissolved ions maintained through complex interactions between atmospheric, terrestrial, and biological processes. Under normal conditions, the ocean's carbonate buffering system maintains pH levels within narrow ranges that allow calcium carbonate-secreting organisms to build and maintain their shells and skeletons. When volcanic acids begin to accumulate in seawater, they overwhelm these natural buffering mechanisms and drive ocean chemistry toward more acidic conditions that prove hostile to marine life. Coral reefs, which represent some of the most diverse and productive ecosystems on Earth, face immediate crisis as acidifying seawater begins to dissolve the calcium carbonate structures that form their physical foundation. The process occurs through simple chemistry as hydrogen ions donated by volcanic acids react with carbonate ions to form bicarbonate, reducing the availability of carbonate ions necessary for coral growth and skeletal maintenance. Coral organisms that have built massive reef structures over thousands of years find their own skeletons beginning to dissolve in the increasingly acidic seawater. The geographic pattern of ocean acidification reflects the distribution of volcanic acid deposition and oceanic circulation patterns. Regions receiving heavy acid rain experience the most severe acidification, while ocean areas connected to these regions through surface currents also begin to show chemical changes as acidified water masses spread through marine circulation systems. The Indian Ocean, which receives substantial acid deposition due to its proximity to the Toba eruption site, experiences particularly severe acidification that affects marine ecosystems across vast areas. Microscopic marine organisms that form the base of oceanic food webs prove especially vulnerable to acidification because many species depend on calcium carbonate for their shell or skeletal structures. Foraminifera, coccolithophores, and pteropods, which collectively represent enormous biomass in marine ecosystems, begin to experience dissolution of their calcium carbonate shells as seawater chemistry shifts beyond their tolerance limits. The decline of these organisms removes crucial links in marine food chains and reduces the efficiency of oceanic carbon cycling. Planktonic communities undergo restructuring as acid-sensitive species decline, while those tolerant of lower pH conditions increase in relative abundance. The changes in plankton community composition affect the entire marine food web, as different plankton species provide different nutritional value and occupy different ecological niches. Fish larvae that depend on specific types of plankton for food during critical developmental stages may find their preferred prey species becoming scarce or unavailable. The photosynthetic organisms that form the base of marine food webs face additional challenges, as reduced sunlight penetration due to volcanic aerosols combines with chemical stress from acidification. Marine phytoplankton, which normally capture solar energy and convert it into biological productivity that supports entire ocean ecosystems, experience reduced photosynthetic efficiency under the dimmed skies created by volcanic particle loading in the atmosphere. Deep ocean circulation patterns begin to change as surface water density increases due to cooling temperatures and altered chemical composition. The formation of dense cold water masses in polar regions drives thermohaline circulation that distributes heat, nutrients, and dissolved gases throughout the global ocean system. When surface water properties change due to volcanic cooling and acidification, the entire oceanic circulation system begins to reorganize in ways that affect marine environments worldwide. Ocean productivity declines as the combined effects of reduced sunlight, altered chemistry, and disrupted circulation patterns create conditions that limit biological activity across multiple trophic levels. Primary productivity by marine phytoplankton decreases as both light availability and chemical conditions become limiting factors for photosynthesis. The reduced primary productivity cascades through marine food webs as organisms at higher trophic levels face declining food availability. Coastal ecosystems experience particularly severe impacts as they receive concentrated inputs of volcanic acids through river discharge and atmospheric deposition, while also being exposed to the biological consequences of declining ocean productivity. Estuarine environments, which serve as nursery habitats for many marine species, face the dual challenge of acidified freshwater inputs from terrestrial sources and acidified seawater from oceanic sources. The chemical stress affects both resident species and those that depend on estuarine habitat for reproduction. Shellfish populations, which include economically and ecologically important species like oysters, clams, and mussels, face direct dissolution of their calcium carbonate shells in acidified seawater. These organisms cannot maintain their protective shells when seawater chemistry shifts beyond certain threshold values, making them vulnerable to predation and environmental stress. The decline of shellfish populations affects both marine food webs and the ecosystem services they provide through filter feeding and habitat creation. Fish populations experience both direct and indirect effects of ocean acidification as their prey species decline and their own physiological processes become stressed by altered water chemistry. Many fish species rely on chemoreception for navigation, prey detection, and predator avoidance. And these sensory systems can be disrupted by changes in seawater chemistry. Behavioral alterations caused by acidification may affect fish survival and reproduction, even when direct toxicity does not occur. Marine mammal populations face cascading effects as their prey species decline, and habitat quality deteriorates due to acidification and associated environmental changes. Whales that depend on planktonic organisms for food may find their feeding grounds becoming less productive as acidification affects the organisms they depend on for survival. The disruption of marine food webs affects marine mammals through complex pathways that may not become apparent until populations begin to decline. How profound that chemical reactions occurring in the stratosphere above Sumatra should alter the pH of seawater in oceans thousands of kilometers away. The ocean acidification demonstrates the global connectivity of Earth's chemical systems and the vulnerability of marine ecosystems to atmospheric perturbations. Seawater that has maintained stable chemistry for geological periods begins to change within years due to volcanic inputs of acid-forming compounds. The buffering capacity of seawater, which normally provides resistance to pH changes, becomes overwhelmed as volcanic acid inputs exceed the natural systems that maintain chemical stability. Carbonate and bicarbonate ions that normally neutralize acids become depleted as they react with volcanic acids, reducing the ocean's ability to resist further acidification. The breakdown of natural buffering systems creates positive feedback effects that accelerate acidification once critical thresholds are exceeded. Paleoceanographic records preserved in marine sediment cores document previous episodes of ocean acidification associated with large volcanic eruptions and provide insight into the long-term consequences of such events. These records suggest that recovery from severe acidification can require thousands of years, as oceanic chemical systems slowly re-equilibrate through weathering processes and biological activity. The sediment cores reveal mass extinction events in marine microfossil assemblages that coincide with evidence of rapid acidification, suggesting that the chemical changes can trigger widespread biological collapse. The spatial heterogeneity of acidification effects creates a complex mosaic of marine environmental conditions, as some ocean regions experience more severe chemical changes than others. Upwelling zones, where deep water rises to the surface, may provide refugia where less acidified water supports biological communities, while enclosed seas and coastal areas experience the most severe impacts. The patchy distribution of acidification effects influences the geographic pattern of marine ecosystem collapse and recovery. Carbonate saturation levels, which determine whether calcium carbonate structures can form or will dissolve, drop below critical thresholds in many ocean regions as acidification progresses. The saturation horizon, below which calcium carbonate dissolves spontaneously, rises toward the surface in many areas, creating vast volumes of seawater that are corrosive to shell-building organisms. The expansion of corrosive water masses eliminates habitat for calcifying species across enormous areas of ocean. The mystery that continues to challenge marine chemists involves understanding the complex interactions between acidification, biological processes, and oceanic circulation that determine the long-term consequences of volcanic acid inputs. While the basic chemistry of acidification is well understood, the biological and physical feedbacks that govern ecosystem responses operate on timescales and spatial scales that make prediction extremely difficult. Each marine ecosystem responds differently to acidification based on its unique biological and chemical characteristics. Yet, across the world's oceans, the chemical transformation proceeds with inexorable persistence. pH levels continue to drop as volcanic acids accumulate in seawater. Carbonate saturation states decline as buffering capacity becomes exhausted. Marine organisms struggle to maintain their calcium carbonate structures in increasingly corrosive seawater. The oceans absorb the sky's poison with the mechanical efficiency of planetary scale chemistry, demonstrating how atmospheric perturbations can fundamentally alter the largest habitat on Earth. Across the volcanic winter's expanding reach, small bands of early humans navigate landscapes transformed beyond recognition by ash, drought, and ecological collapse. These populations of Homo sapiens, numbering perhaps in the tens of thousands across the entire African and Eurasian continents, possess the cognitive flexibility and technological sophistication necessary to adapt to rapidly changing environmental conditions. But even their remarkable adaptability faces unprecedented challenges as familiar ecosystems disappear and reliable resources become scarce. The human populations living closest to the Toba eruption site face immediate crisis as volcanic ashfall buries their familiar landscapes under meters of abrasive debris. The technological adaptations that have allowed humans to colonize diverse environments, fire use, tool manufacture, shelter construction, cooperative hunting, provide some protection against the immediate effects of ashfall, but cannot shield them from the long-term consequences of ecosystem collapse and resource scarcity that follow the eruption. Archaeological evidence suggests that human populations were already sparse and widely scattered at the time of the Toba eruption, with small groups occupying favorable locations across Africa, the Middle East, and Southern Asia. These populations likely numbered in the hundreds or low thousands per regional group, making them extremely vulnerable to environmental perturbations that reduce carrying capacity below the minimum levels necessary to maintain viable breeding populations. The cognitive abilities that distinguish Homo sapiens from other hominin species, complex language, abstract thinking, technological innovation, social cooperation, become crucial survival tools during the volcanic winter. Human groups can communicate information about changing environmental conditions, develop new technologies to exploit novel food sources, coordinate resource sharing across extended social networks, and make collective decisions about migration and adaptation strategies. Tool technologies undergo rapid evolution as human groups encounter new challenges and opportunities created by environmental change. Traditional hunting weapons and food processing tools must be adapted for use in ash-covered landscapes where normal prey species have become scarce. Stone tool assemblages begin to show modifications that reflect changing resource availability and the need to process previously unexploited food sources. Fire technology becomes even more critical for human survival as environmental conditions deteriorate and conventional food sources become scarce. The ability to create and maintain fire allows humans to cook tough plant materials that would otherwise be indigestible, extend the usability of meat through smoking and cooking, provide warmth during periods of reduced temperature, and create social gathering spaces that maintain group cohesion during stressful periods. Shelter construction takes on increased importance as environmental conditions become more severe and unpredictable. Human groups must develop new architectural solutions for protection against ashfall, altered precipitation patterns, and temperature extremes created by the volcanic winter. The construction of more substantial shelters requires increased cooperation and resource investment, but provides essential protection against environmental hazards. Social organization becomes crucial for survival, as resource scarcity increases competition within and between human groups, while also requiring greater cooperation for successful adaptation. The balance between competition and cooperation that characterizes human societies faces severe testing, as groups must decide whether to share scarce resources with neighbors or reserve them for their own survival. These decisions have immediate consequences for group survival and long-term implications for population genetics. Migration patterns change dramatically as human groups abandon areas where environmental degradation has reduced carrying capacity below viable levels and move toward regions that retain sufficient resources to support human populations. The movement of people across landscapes creates new patterns of cultural contact and genetic exchange, while also increasing competition for remaining favorable habitats. Dietary adaptations become essential as traditional food sources disappear or become unreliable due to ecosystem changes. Human groups must identify and exploit new plant and animal resources while developing processing techniques to make marginal foods usable. The expansion of dietary breadth requires both technological innovation and cultural transmission of knowledge about new food sources and processing methods. Coastal populations may enjoy some advantages during the volcanic winter, as marine resources prove more reliable than terrestrial ones in many regions. However, ocean acidification and reduced marine productivity create challenges even for coastal groups. And the specialized knowledge required for effective marine resource exploitation may not be available to inland populations that attempt to move toward coastal areas. The demographic consequences of the volcanic winter create population bottlenecks that affect human genetic diversity for thousands of years into the future. Small population sizes increase the probability of genetic drift and inbreeding, while reducing the genetic variation available for adaptation to new environmental challenges. Population crashes can eliminate genetic lineages entirely, creating founder effects when populations recover from small surviving groups. Reproductive strategies undergo modification as environmental stress affects fertility and child survival rates. The energy requirements for successful reproduction increase under harsh environmental conditions while available resources decline, creating conflicts between immediate survival needs and long-term reproductive success. Human groups must balance current survival against future population growth in making decisions about resource allocation and reproductive timing. Cultural transmission systems face challenges as environmental stress disrupts normal patterns of learning and knowledge transfer between generations. Elders who possess critical environmental knowledge may not survive the environmental crisis, while young people who would normally learn traditional skills may be required to focus on immediate survival needs rather than long-term cultural learning. Technological innovation accelerates under the pressure of environmental change as human groups develop new solutions to novel survival challenges. However, the small population sizes and social disruption created by environmental stress can also impede innovation by reducing the number of individuals available to develop and test new technologies, and by disrupting social networks that facilitate knowledge sharing. How remarkable that the cognitive abilities that evolve to help humans navigate complex social environments should prove essential for survival during planetary-scale environmental catastrophe. The same mental capacities that enable humans to create art, develop language, and build complex societies also provide the flexibility necessary to adapt rapidly to environmental conditions that exceed anything in their evolutionary history. The geographic distribution of human survival during the volcanic winter likely reflects both environmental conditions and pre-existing population characteristics. Groups that were already adapted to marginal environments may prove more resilient to further environmental degradation, while populations living in previously optimal habitats may lack the cultural and technological adaptations necessary for survival under harsh conditions. Social memory systems that preserve information about past environmental changes become crucial resources during the volcanic winter, as human groups must draw upon any available knowledge about survival strategies during difficult periods. Oral traditions, technological knowledge, and environmental lore transmitted across generations provide templates for adaptation that may mean the difference between survival and extinction. The mystery that continues to fascinate anthropologists involves understanding how human populations managed to survive environmental catastrophes that eliminated many other large mammal species. While humans possessed unique cognitive and technological advantages, they also face the same basic biological constraints as other species in terms of energy requirements, reproductive needs, and environmental tolerances. Yet scattered across the ash-covered continents, small groups of humans continue their struggle for survival against odds that challenge the limits of human adaptability. They modify their technologies, adjust their social systems, expand their dietary repertoires, and migrate toward remaining refugia. Their survival depends not only on individual adaptability, but on collective decision-making and social cooperation that allows groups to function effectively under extreme environmental stress. The volcanic winter tests not just human biology, but human culture, challenging both the physical and social adaptations that distinguish our species from all others that have walked on Earth. The fossil record that forms during the volcanic winter years preserves a stark chronicle of biological disappearance across multiple continents and ecosystems. Species that evolved over millions of years vanish from the geological record within decades, leaving behind only fragmentary remains and empty ecological niches that speak to the magnitude of environmental disruption. The pace of extinction accelerates as cascading ecological failures eliminate entire genera and families of organisms that cannot adapt rapidly enough to survive the altered environmental conditions. Large mammal populations, which require extensive habitat areas and abundant food resources to maintain viable populations, prove particularly vulnerable to the combined effects of habitat loss, climate change, and resource scarcity. Megafauna species that survived previous environmental challenges succumb to the sustained environmental pressure created by volcanic winter conditions that persist for years beyond their adaptive capacity. Elephants, rhinoceros, large cats, and herbivorous ungulates disappear from vast areas where they have existed for hundreds of thousands of years. The extinction patterns show clear geographic variation that reflects the spatial distribution of environmental impacts and the pre-existing vulnerability of different populations. Species living in marginal habitats or those already stressed by natural environmental variation prove most susceptible to the additional pressure created by volcanic forcing. Island populations, which often exist as small, isolated communities with limited genetic diversity, experience particularly high extinction rates as their restricted habitats undergo rapid environmental change. Carnivore populations face cascading impacts as their prey species decline or disappear entirely from affected ecosystems. Large predators that depend on specific prey species find themselves without adequate food sources as herbivore populations crash under the pressure of vegetation dieback and habitat loss. The complex predator-prey relationships that have structured ecosystems for millions of years unravel as the foundational species that support food webs disappear from degraded landscapes. Plant communities experience mass mortality events that eliminate entire taxonomic groups from regional floras. Endemic species with restricted distributions and specialized habitat requirements prove unable to survive the rapid environmental changes and lack the geographic range necessary to track suitable habitat conditions as climate zones shift. The loss of plant diversity creates cascading effects throughout terrestrial ecosystems as the primary productivity that supports all other life forms declines dramatically. Aquatic ecosystems undergo their own extinction crises as acidification, temperature changes, and altered precipitation patterns combine to create conditions that exceed the tolerance limits of many freshwater and marine species. Fish populations that depend on specific water chemistry conditions find their habitat becoming unsuitable for survival and reproduction. Amphibians, which possess permeable skin that makes them particularly sensitive to chemical changes, experience widespread population crashes across multiple species and geographic regions. Insect communities, which represent the most diverse group of organisms on Earth, face unprecedented challenges as their host plants disappear and microhabitat conditions change rapidly. Many insect species depend on specific plant species for food and reproduction, creating co-evolutionary relationships that cannot survive the disappearance of either partner. The loss of insect diversity affects pollination networks and decomposer communities that provide essential ecosystem services. Endemic species that evolved in isolation on islands or in specialized habitats face complete extinction as their restricted distributions provide no opportunities for range shifts or habitat tracking. These evolutionary unique species represent millions of years of independent evolution, and their extinction eliminates entire evolutionary lineages that can never be reconstructed. The loss of endemic biodiversity represents an irreversible reduction in the complexity of life on Earth. Microbial communities undergo dramatic reorganization as soil conditions change and organic matter inputs shift in response to vegetation dieback. While microorganisms generally show greater resilience to environmental change than larger organisms, the massive inputs of dead plant material and altered soil chemistry create conditions that favor different microbial assemblages. The changes in soil microbial communities affect nutrient cycling and soil formation processes for centuries after the initial environmental perturbation. Marine planktonic communities experience mass mortality events as ocean acidification and reduced primary productivity create unsuitable conditions for many species. The microscopic organisms that form the base of marine food webs disappear from large ocean areas, creating cascading effects that propagate through entire marine ecosystems. The extinction of key planktonic species disrupts oceanic carbon cycling and reduces the efficiency of marine biological processes. Pollinator networks collapse as both plant and animal species that participate in pollination relationships experience population declines that prevent successful reproduction. The coevolutionary relationships between flowers and their pollinators, refined over millions of years of mutual adaptation, break down when either partner becomes too rare to maintain viable interaction networks. The failure of pollination systems prevents plant reproduction even among surviving plant populations. Seed dispersal networks face similar disruption as frugivorous animals that transport seeds between habitat patches disappear from degraded ecosystems. Many plant species depend on specific animal dispersers for long-distance seed transport, and the extinction of these animal partners eliminates the possibility of plant colonization of new habitat areas. The breakdown of seed dispersal networks prevents ecosystem recovery even when environmental conditions begin to improve. The genetic consequences of population crashes create long-term effects that persist long after environmental conditions have returned to normal. Small population sizes that result from environmental stress lead to genetic bottlenecks that reduce genetic diversity and increase the probability of inbreeding depression. Surviving populations may lack the genetic variation necessary to adapt to future environmental challenges, making them vulnerable to subsequent perturbations. How tragic that relationships forged over millions of years of coevolution should dissolve within decades due to environmental changes that operate faster than biological adaptation can respond. The mass extinctions demonstrate the vulnerability of complex biological systems to rapid environmental change and the difficulty of maintaining biodiversity when fundamental environmental parameters shift beyond the range of natural variation. Refugial populations that survive in protected microhabitats or favorable geographic locations become the genetic repositories from which future ecosystem recovery must proceed. These surviving populations often represent only a small fraction of the original genetic and taxonomic diversity, creating founder effects that influence the structure of recovering ecosystems for thousands of years. The species that survive the volcanic winter are not necessarily those best adapted to normal environmental conditions, but rather those that possess the flexibility or fortune necessary to survive extreme environmental stress. The extinction selectivity shows clear patterns related to body size, habitat requirements, reproductive strategies, and geographic distribution. Species with large body sizes, specialized habitat needs, slow reproductive rates, and restricted distributions prove most vulnerable to extinction, while small, generalist species with rapid reproductive rates and wide distributions show greater survival probability. These patterns reflect the different ways that environmental stress affects organisms with different life history characteristics. Ecosystem function undergoes fundamental alteration as key species disappear and the biological processes they performed are eliminated from ecological communities. Decomposition rates change as decomposer species are lost. Nutrient cycling is disrupted as plants and soil organisms that mediate biogeochemical processes disappear. Primary productivity declines as photosynthetic organisms are eliminated from degraded habitats. The mystery that continues to challenge conservation biologists involves understanding the mechanisms that determine which species survive mass extinction events and which disappear forever. While general patterns of extinction selectivity are apparent, the specific factors that allow some populations to persist while closely related ones vanish remain difficult to predict. Each extinction event provides unique insights into the factors that influence species survival. But the rarity of such events limits opportunities for comparative study. Yet, across the continents, the fossil record continues to accumulate the evidence of biological disappearance as species after species crosses the threshold from rarity to extinction. Skeletal remains and fossilized plant parts preserve the final moments of evolutionary lineages that stretched back millions of years. Empty habitat niches mark the former presence of species that once filled essential ecological roles. The volcanic winter writes its signature in the fossil record through absence rather than presence, through the spaces where life once flourished but will never return. In the scattered refugia where environmental conditions remain within the bounds of biological tolerance, life begins its slow process of reorganization and recovery. These refugial areas, protected valleys with reliable water sources, coastal regions buffered by oceanic thermal stability, cave systems that provide shelter from surface environmental extremes, become the genetic and ecological repositories from which future ecosystems must be reconstructed. The recovery process operates according to ecological principles that favor certain types of organisms while creating barriers for others, ultimately reshaping the biological communities that emerge from their volcanic winter. The spatial distribution of refugia reflects the complex interaction between regional topography, local climate patterns, and the specific environmental tolerances of different species. Mountain valleys that channel moisture from higher elevations maintain sufficient water availability to support plant communities, even as surrounding areas experience severe drought. Coastal areas benefit from the thermal buffering effect of large water bodies that moderate temperature extremes and maintain more stable climatic conditions than continental interiors. Primary succession begins in areas where volcanic ashfall has completely buried existing ecosystems, creating novel substrate conditions that must be colonized by organisms capable of surviving on mineral-rich but nutrient-poor volcanic soils. The first colonizing species typically include pioneering plants with rapid growth rates, efficient seed dispersal mechanisms, and the ability to establish symbiotic relationships with nitrogen-fixing bacteria that can provide essential nutrients in nutrient-poor environments. Pioneer plant communities that establish on volcanic ash deposits possess characteristics that distinguish them from the forest communities they replace. These early successional species typically show rapid growth, high reproductive output, efficient resource capture, and tolerance for the harsh chemical and physical conditions created by fresh volcanic deposits. Grasses, ferns, and small shrubs often dominate early recovery communities due to their ability to quickly exploit available resources and reproduce successfully under marginal conditions. Soil development proceeds slowly in ash-covered areas as physical and chemical weathering processes begin to break down volcanic glass particles and create the soil structure necessary for supporting more complex plant communities. The transformation of sterile volcanic ash into productive soil requires decades to centuries and depends on the activities of soil organisms, water movement, and chemical weathering processes that operate at rates determined by temperature, precipitation, and biological activity. Recolonization of recovering areas depends on the presence of nearby source populations and the existence of dispersal corridors that allow organisms to move from refugial areas to sites where habitat conditions are improving. Seeds, spores, and mobile animals from surviving populations gradually spread into recovering areas. But the process occurs slowly and may require centuries for complete ecosystem restoration. The distance between refugia and recovering areas often determines which species can successfully recolonize and which remain absent from restored ecosystems. Animal communities recover through complex processes that depend on the restoration of habitat structure, food web relationships, and breeding sites necessary for successful reproduction. Herbivorous species can begin to recolonize areas only after sufficient plant biomass has accumulated to support their nutritional needs. Carnivorous species require the prior establishment of adequate prey populations, creating a temporal sequence of recovery that proceeds from primary producers through herbivores to predators. The genetic consequences of population bottlenecks become apparent during the recovery process, as surviving populations expand from small founder groups with reduced genetic diversity. Genetic drift and founder effects influence the characteristics of recovering populations, potentially eliminating genetic variants that might be important for future adaptation. The genetic composition of recovering populations may differ substantially from pre-extinction communities due to the random sampling effects that operate during severe population bottlenecks. Invasive species dynamics become important during ecosystem recovery, as disturbed habitats provide opportunities for colonization by species that were previously excluded by established biological communities. The breakdown of natural community structure during the extinction event creates ecological opportunities for species that can exploit disturbed conditions, potentially leading to the establishment of novel community assemblages that differ from pre-disturbance ecosystems. Island biogeography principles govern the recovery process, as refugial areas function as islands of suitable habitat, surrounded by areas where environmental conditions remain unsuitable for most species. The size of refugial areas influences their capacity to maintain viable populations during the extinction event, while their isolation affects the rate at which species can spread from refugia to recovering areas. Larger refugia support more species and provide greater genetic diversity for ecosystem recovery. Keystone species play crucial roles in ecosystem recovery by providing ecological services that facilitate the establishment and survival of other species. Nitrogen-fixing plants that can establish on nutrient-poor volcanic soils create conditions that allow other plant species to colonize these areas. Large herbivores that survive in refugial areas can disperse seeds across recovering landscapes as they expand their ranges into improving habitats. Mycorrhizal fungi that form symbiotic relationships with plant roots become essential for ecosystem recovery in areas where soils have been sterilized by volcanic processes. These fungal networks must be re-established before many plant species can successfully colonize volcanic ash deposits, creating dependencies that influence the sequence and rate of ecosystem recovery. The restoration of below-ground fungal communities often limits the rate at which above-ground plant communities can recover. Restoration of ecosystem function proceeds more slowly than the recovery of species diversity, as the complex ecological relationships that govern ecosystem processes require time to re-establish. Nutrient cycling rates remain low until decomposer communities recover and organic matter accumulates in developing soils. Primary productivity increases gradually as plant communities develop more complex structure and efficiency in resource utilization. The temporal sequence of recovery shows predictable patterns as ecological succession proceeds from simple pioneer communities through intermediate stages toward more complex mature ecosystems. However, the recovery process may not lead to exact restoration of pre-extinction communities due to the stochastic effects of colonization, genetic changes in surviving populations, and altered environmental conditions that persist after the initial disturbance. Climate stability becomes crucial for successful ecosystem recovery, as recovering communities need time to establish without facing additional major environmental perturbations. The gradual clearing of volcanic aerosols from the atmosphere allows solar radiation to return to normal levels, providing the energy necessary for photosynthesis and primary productivity. Precipitation patterns slowly return to normal as atmospheric circulation systems readjust to post-volcanic conditions. How remarkable that life's capacity for recovery should emerge from such devastating destruction, demonstrating the resilience of biological systems and the power of natural selection to reshape communities in response to environmental change. The recovery process shows both the fragility of complex ecological relationships and the persistence of life's fundamental processes under even extreme environmental conditions. The rate of recovery varies dramatically among different types of ecosystems and organisms, creating a temporal mosaic of ecological restoration that may persist for thousands of years. Grassland and shrubland communities typically recover more rapidly than forest ecosystems due to their simpler structure and faster reproductive rates of constituent species. Aquatic ecosystems may recover quickly if water quality returns to acceptable levels, but may show persistent changes if chemical alterations have permanently affected habitat conditions. Ecosystem services that human populations depend on for survival begin to return as ecological communities recover. But the restoration of these services may lag behind the recovery of species diversity, soil formation, water filtration, pollination services, and climate regulation require the reestablishment of complex ecological processes that operate at ecosystem scales. The human populations that survive the volcanic winter depend on the recovery of these ecosystem services for their long-term persistence and cultural development. The mystery that continues to fascinate ecologists involves understanding the factors that determine whether ecosystem recovery leads to restoration of pre-disturbance communities or to the development of novel ecosystem states. While ecological succession follows predictable general patterns, the specific outcomes of recovery processes depend on the particular combination of surviving species, environmental conditions, and chance colonization events that characterize each recovering system. Yet in quiet corners where conditions allow, life begins its patient work of restoration. Seeds germinate in protected microsites. Surviving animals venture from refugial areas into improving habitats. Soil organisms begin the slow process of rebuilding the biological infrastructure that supports terrestrial ecosystems. Recovery proceeds with the same persistence that characterized the initial destruction. Following ecological laws that favor adaptation and resilience while honoring the memory of what was lost through the patient construction of what might yet be, deep within the genetic architecture of surviving organisms. The molecular signatures of the Toba catastrophe begin to accumulate as populations crash to sizes where random genetic drift overwhelms natural selection, and founder effects reshape the hereditary material that will define future generations. These genetic bottlenecks created when large populations contract to small numbers of breeding individuals, leave permanent marks in DNA sequences that scientists thousands of years in the future will read like historical documents recording one of the most severe population crashes in human evolutionary history. Human populations, which may have numbered in the hundreds of thousands before the eruption, contract to perhaps 10,000 breeding individuals scattered across Africa and southern Asia in isolated groups that maintain only limited contact with each other. The dramatic reduction in population size creates conditions where genetic diversity is lost rapidly through random sampling effects that operate when small numbers of individuals contribute genes to the next generation. Rare genetic variants disappear entirely from the human gene pool, while common variants become fixed at high frequencies through the random processes that dominate small population genetics. The mitochondrial DNA lineages that trace maternal inheritance through human populations show clear evidence of a severe bottleneck coinciding with the Toba eruption timeline. Modern human mitochondrial diversity stems from a small number of maternal lineages that survived the population crash, suggesting that human females capable of reproduction during the volcanic winter numbered in the hundreds rather than thousands. The molecular clock calculations based on mitochondrial DNA mutation rates point to a population bottleneck of extraordinary severity that nearly eliminated our species entirely. Y chromosome lineages that trace paternal inheritance show similar patterns of diversity loss and rapid expansion from small founder populations. The genetic evidence suggests that effective male population size during the bottleneck dropped to levels where only a few dozen breeding males contributed genes to subsequent generations. This extreme reduction in breeding population size created conditions where genetic drift could eliminate entire chromosomal lineages and dramatically alter allele frequencies across the human genome. Nuclear DNA sequences preserve additional evidence of the population bottleneck through patterns of linkage disequilibrium and reduced heterozygosity that characterize populations that have passed through severe demographic contractions. The human genome shows signatures of a population expansion from a small founder group, with genetic diversity patterns that indicate rapid population growth following a severe bottleneck. These genomic signatures provide independent confirmation of the demographic crash inferred from archaeological and paleoclimatic evidence. The geographic distribution of genetic diversity in modern human populations reflects the spatial pattern of survival during the volcanic winter and the subsequent expansion of human populations from refugial areas. African populations retain the highest levels of genetic diversity, suggesting that this continent provided the most favorable conditions for human survival during the crisis. Asian populations show evidence of founder effects and genetic drift that indicate colonization by small groups expanding from African refugia. Founder effects become apparent in the genetic composition of populations that survived in different refugial areas, as random sampling during population bottlenecks creates distinctive genetic signatures in geographically separated groups. Populations that survived in different refugia developed characteristic allele frequencies and genetic variants that reflect the particular combination of individuals who survived in each location. These founder signatures persist for thousands of years and influence the genetic structure of populations that descend from bottleneck survivors. Inbreeding depression begins to affect surviving populations as mating between relatives becomes unavoidable in small, isolated groups where most individuals share recent common ancestors. The expression of deleterious recessive alleles increases as inbreeding coefficients rise, reducing fertility and survival rates in populations that are already struggling with environmental stress. The genetic consequences of inbreeding create additional challenges for population recovery beyond those imposed by continued environmental hardship. Loss of genetic diversity affects the adaptive potential of surviving populations by reducing the raw material available for natural selection to act upon in response to environmental challenges. Genetic variants that might prove beneficial under future environmental conditions may have been eliminated during the bottleneck, permanently reducing the evolutionary flexibility of human populations. The genetic consequences of the bottleneck constrain human evolutionary potential for thousands of years into the future. Population genetics models suggest that recovery from such severe bottlenecks requires thousands of years to restore genetic diversity through new mutations and population expansion. The human populations that emerge from the volcanic winter carry reduced genetic variation that affects disease resistance, reproductive success, and adaptive capacity for dealing with environmental change. The genetic legacy of the Toba bottleneck influences human biology and evolution for tens of thousands of years following the initial population crash. Comparative studies of other mammalian species show similar genetic signatures of population bottlenecks coinciding with the Toba timeline, suggesting that the demographic impacts extended across multiple species and ecosystems. Large mammal populations that survived the volcanic winter show evidence of genetic diversity loss and founder effects similar to those observed in human populations. The molecular evidence confirms that the environmental crisis affected entire biological communities rather than just single species. Genetic rescue effects may have occurred in some populations as surviving groups from different refugia eventually re-established contact and gene flow, introducing new genetic variants and reducing inbreeding depression. However, the exchange of genetic material between separated populations likely occurred slowly over many generations, as human groups gradually expanded from refugial areas and re-established contact with distant relatives. The selection pressures operating during the volcanic winter may have favored certain genetic variants that enhanced survival under extreme environmental conditions while eliminating others that were neutral or beneficial under normal circumstances. Alleles that improved cold tolerance, enhanced immune function, or increased metabolic efficiency might have increased in frequency during the crisis, even as overall genetic diversity declined. The combination of genetic drift and natural selection reshaped human genetic composition in ways that influenced subsequent evolution. Epigenetic modifications that alter gene expression without changing DNA sequences may have allowed rapid adaptation to volcanic winter conditions within the lifespans of individual survivors. Stress-induced changes in gene regulation could have enhanced survival and reproduction under harsh environmental conditions while being transmitted to offspring through epigenetic inheritance mechanisms. These regulatory changes provide a mechanism for rapid adaptation that complements the slower process of genetic evolution. How profound that molecular changes occurring within individual cells should preserve historical records of planetary-scale environmental catastrophe, demonstrating the intimate connection between geological processes and biological evolution. The genetic bottlenecks created by the Toba eruption represent one of the most severe demographic crashes in human evolutionary history, leaving molecular scars that persist in the human genome for tens of thousands of years after the volcanic ash has settled and the climate has returned to normal. The timing of genetic diversity loss inferred from molecular clock analyses aligns closely with geological evidence for the Toba eruption, providing independent support for the hypothesis that volcanic winter conditions created severe demographic bottlenecks in human and other mammalian populations. The convergence of genetic, archaeological, and geological evidence creates a compelling case for a direct causal relationship between the supervolcanic eruption and near extinction of early human populations. Modern human genetic diversity patterns continue to reflect the geographic distribution of survival during the volcanic winter, as populations that experience the most severe bottlenecks show the least genetic variation, while those that survived in more favorable refugial areas retain higher levels of diversity. The genetic legacy of the crisis influences modern human population genetics and provides insights into the demographic history of our species. The mystery that continues to challenge population geneticists involves understanding how human populations manage to survive such severe demographic bottlenecks when many other large mammal species experienced complete extinction. While genetic evidence clearly documents the severity of human population crashes, it also demonstrates the remarkable resilience that allowed small founder populations to recover and ultimately colonize the entire planet. Yet within the DNA of every living human, the molecular memory of that ancient crisis persists in patterns of genetic variation that speak to our species' brush with extinction. The genetic bottlenecks tell their story through missing diversity, through lineages that vanished forever, through the narrow genetic foundation upon which all subsequent human evolution has been built. The volcanic winter left its signature not just in ice cores and rock layers, but in the very molecules that define human biological inheritance, creating a genetic monument to survival against impossible odds. Above the collapsed volcanic crater that will one day become Lake Toba, rainwater begins its patient work of filling the vast depression left by the eruption that changed the world. The process unfolds with a geological slowness as precipitation accumulates in the caldera, creating first small pools, then interconnected ponds, and eventually a single body of water that will grow to become one of Earth's largest volcanic lakes. The formation of the lake represents not destruction, but transformation. The violent cavity created by explosive eruption becomes a reservoir of tranquility that will persist for thousands of years. The early stages of lake formation occur as seasonal rains fill the caldera floor with water that has no outlet to the sea. The volcanic debris that lines the crater bottom proves remarkably impermeable to water flow, creating natural dam conditions that allow precipitation to accumulate rather than drain away through underground channels. The chemistry of this early lake water reflects the interaction between rainwater and fresh volcanic ash, creating a mineral-rich environment unlike any normal freshwater system. Dissolved minerals leached from volcanic ash create water chemistry conditions that initially prove hostile to most aquatic life. High concentrations of dissolved aluminum, sulfur compounds, and other volcanic elements create acidic conditions that prevent the establishment of normal freshwater biological communities. The lake exists for decades as a sterile chemical system where only the most tolerant microorganisms can survive in water that would prove toxic to most aquatic species. Gradually, as weathering processes neutralize the most toxic chemical components and dilution reduces mineral concentrations to more tolerable levels, the lake begins to support simple biological communities. Bacteria and algae that can tolerate the unique chemical conditions begin to establish populations in the lake water. These pioneering organisms begin the process of biological colonization that will eventually transform the sterile volcanic lake into a complex aquatic ecosystem. The lake's depth increases slowly as continued precipitation and runoff from the surrounding watershed add water faster than it can be lost through evaporation. The tropical climate of Sumatra ensures abundant rainfall that maintains positive water balance conditions throughout most years. The lake level rises gradually over centuries, submerging volcanic debris and creating an increasingly large body of water that begins to moderate the local climate through its thermal mass. Sediment accumulation on the lake bottom begins immediately as erosion of the caldera walls and volcanic ash deposits provides a steady supply of fine particles that settle through the water column. These early sediment layers preserve a detailed record of environmental conditions during the lake's formation, including evidence of continued volcanic activity, climate variations, and the gradual establishment of biological communities in and around the developing lake. The first fish populations arrive through river connections that develop as the lake level rises high enough to create overflow channels connecting the caldera to external drainage systems. These early colonizing fish species must possess broad tolerance ranges that allow them to survive in the lake's unique chemical environment. The establishment of fish populations marks a major transition in lake ecosystem development as vertebrate predators begin to structure aquatic food webs. Aquatic plants begin to colonize shallow areas of the lake as water chemistry conditions improve and sufficient light penetrates to the lake bottom to support photosynthesis. The establishment of rooted vegetation provides habitat structure that supports increasingly complex biological communities. Submerged and emergent plants create nursery areas for fish reproduction and feeding habitat for waterfowl that begin to visit the developing lake ecosystem. The lake's thermal properties begin to influence local climate as the large volume of water moderates temperature fluctuations and creates convective patterns that affect regional precipitation. Lake effect weather patterns develop as air masses moving across the water surface gain or lose moisture depending on seasonal temperature differences between the lake and surrounding land areas. The lake becomes an active component of regional climate systems, rather than simply a passive recipient of atmospheric inputs. Wetland ecosystems develop around the lake margins as water level fluctuations create zones of periodic inundation that support specialized plant communities adapted to alternating wet and dry conditions. These marginal wetlands provide critical habitat for waterfowl, amphibians, and other species that require both aquatic and terrestrial habitat elements for their life cycles. The wetland areas also serve as biological filters that process nutrients and sediments before they enter the main lake basin. Human populations begin to discover and utilize the lake resources as the ecosystem develops sufficient productivity to support fishing and other extractive activities. The lake provides reliable water supplies in a region where surface water can be scarce during dry seasons. Early human settlements around the lake take advantage of both aquatic resources and the more predictable water supplies that support agriculture in areas adjacent to the lake. Cultural traditions develop around the lake as human communities establish long-term relationships with this unique landscape feature. The dramatic origin of the lake through a volcanic catastrophe likely influences local mythology and religious practices. Though the specific cultural responses develop slowly over many generations of human occupation, the lake becomes integrated into human cultural landscapes as both a practical resource and a symbolic landmark. Geological processes continue to shape the lake and its surroundings as volcanic activity persists at low levels and erosional processes gradually modify the caldera structure. Small earthquakes occasionally affect the lake as continued subsidence and magma movement create ground motion that can trigger landslides or alter drainage patterns. The lake exists within an active geological system where ongoing volcanic processes continue to influence its physical and chemical characteristics. The biodiversity of the lake ecosystem increases gradually as more species colonize the habitat and ecological relationships become more complex. Endemic species begin to evolve as populations become isolated in the unique lake environment and undergo genetic divergence from their ancestral forms. The lake's large size and chemical distinctiveness create conditions that favor the evolution of species found nowhere else on Earth. Nutrient cycling patterns develop as biological communities become established and begin to process organic matter and mineral inputs according to the ecological principles that govern all aquatic ecosystems. Primary productivity by phytoplankton and aquatic plants provides the energy base that supports increasingly complex food webs. Decomposer organisms recycle nutrients from dead organic matter, maintaining the chemical cycles necessary for sustained biological productivity. The lake's sediment record begins to preserve detailed environmental archives as biological productivity increases and seasonal cycles become established. Annual layers of sediment accumulation record variations in precipitation, temperature, volcanic activity, and biological productivity that create a continuous record of environmental change. These sediment cores will eventually provide scientists with detailed information about regional climate history and ecosystem development. Water quality gradients develop within the lake as different areas experience varying influences from tributary inputs, volcanic activity, and biological processes. Shallow areas near shore typically show different chemical characteristics than deep central areas, creating habitat diversity that supports different biological communities. The three-dimensional structure of water quality variation provides multiple ecological niches that enhance overall biodiversity. Seasonal cycles become established as the lake ecosystem responds to annual patterns of precipitation, temperature, and solar radiation that characterize the tropical climate. Wet and dry season differences affect lake level, nutrient inputs, and biological activity in predictable annual patterns. The development of seasonal predictability allows biological communities to evolve life cycle timing that takes advantage of favorable conditions and avoids stressful periods. The lake's influence on local hydrology extends beyond its immediate basin, as the large water body affects groundwater patterns and provides base flow for streams that drain from the caldera area. Springs develop around the lake margins where groundwater emerges after interacting with volcanic rocks and lake water. These springs often have unique chemical characteristics that support specialized biological communities. Island formation occurs as volcanic activity creates new land areas within the lake, or as erosional processes isolate portions of the original caldera rim. Samosir Island, which will become a major feature of the mature lake, develops as continued volcanic activity and differential subsidence create a large island in the central portion of the lake. These islands provide isolated habitat that promotes additional endemic evolution and adds structural complexity to the lake ecosystem. Commercial fisheries begin to develop as human populations grow and fish populations become large enough to support sustained harvest. Traditional fishing methods evolve to take advantage of the lake's unique characteristics and fish community composition. The development of fisheries creates economic incentives for continued human settlement around the lake and influences the cultural development of lakeside communities. The lake's role as a regional landmark becomes important for navigation and territorial organization as human populations expand and establish more complex social systems. The distinctive circular shape and large size make the lake visible from great distances and useful as a reference point for travel and trade. Cultural significance develops around the lake's distinctive origin and prominent position in the regional landscape. How remarkable that the same geological processes that created one of Earth's most devastating natural disasters should ultimately produce one of its most serene and beautiful landscapes. The transformation from volcanic violence to peaceful lake demonstrates nature's capacity for healing and renewal. Even after catastrophic destruction, the lake that forms above the sleeping volcano becomes a symbol of resilience and recovery that transcends the original catastrophe. The mystery that continues to fascinate limnologists involves understanding how such large volcanic lakes develop their unique ecological characteristics and maintain long-term stability despite their origin in highly unstable geological environments. While the basic processes of lake formation and ecosystem development are well understood, each volcanic lake develops distinctive features that reflect its particular geological setting and environmental history. Scientific studies of the mature lake will eventually reveal its complex internal structure, with thermally stratified water masses, diverse biological communities, and ongoing geological activity that continues to influence lake characteristics. The lake serves as a natural laboratory for studying the interactions between geological and biological processes over long time scales. Researchers find in Lake Toba a unique ecosystem that preserves records of both catastrophic change and gradual recovery. Tourist development around the mature lake creates economic opportunities for local communities, while also creating challenges for environmental protection and cultural preservation. The lake's beauty and cultural significance attract visitors from around the world, generating income for local communities but also creating pressure on natural resources and traditional ways of life. The balance between development and conservation becomes an ongoing challenge for lake management. Yet, above the ancient crater, the lake continues its quiet existence as one of Earth's most peaceful and beautiful water bodies. Fishermen cast their nets into waters that once boiled with molten rock. Children swim in the shallows where volcanic gases once escaped from the depths. Villages cluster along shores that mark the boundaries of a caldera created by planetary violence. The lake holds its memories in sediment layers and bathymetry, but its surface reflects only sky and clouds, offering tranquility to a landscape that has known ultimate destruction and emerged transformed into something entirely new. The formation of Lake Toba represents more than simple geological recovery. It demonstrates the fundamental creativity of natural processes that can transform destruction into beauty, catastrophe into peace, and violent endings into serene beginnings. The lake that sleeps above the supervolcano becomes a meditation on the passage of time and the power of natural processes to heal even the most devastating wounds that Earth can inflict upon itself. The volcanic winter gradually releases its grip on the world as stratospheric aerosols settle under gravitational influence and solar radiation slowly returns to normal intensity across the continents. Surviving ecosystems begin their patient work of recovery while the genetic memory of survival rests secure within the DNA of species that endured the trial of fire and ice. The lake grows deeper and more peaceful with each passing season, its surface reflecting clouds that drift through skies no longer darkened by volcanic haze. In laboratories that exist only in the distant future, scientists will extract ice cores from Greenland and Antarctica, reading in frozen atmospheric chemistry the precise chemical signature of this ancient catastrophe. They will find volcanic glass and sediment cores from ocean floors around the world, each microscopic fragment carrying the molecular fingerprint of Sumatra across thousands of kilometers and millions of years. The story will be written in ash layers and genetic bottlenecks, in extinct species and empty ecological niches, in the very atoms that make up the modern world. But here, in the slow rhythm of geological time, the immediate drama fades into the patient work of recovery and renewal. Seeds germinate in volcanic soil, rivers carve new channels through ash deposits. Life adapts, persists, and gradually flourishes once again. The supervolcano sleeps beneath its lake, dreaming perhaps of the day when internal pressures might again reach critical thresholds, but for now content to rest in the tranquil depths of geological time. The lake reflects the sky like a mirror of forgiveness, holding in its depths the memory of violence transformed into peace. Around its shores, the world continues its eternal dance of change and continuity, destruction and creation, ending and beginning. In the end, there is only the water, the sky, and the slow, eternal heartbeat of the sleeping giant below.